For up to 8 hours, it tells you every time you start a Hangout on air. Welcome, people. How are you doing today? So I have with me today TrueEmpiricism, well known as Roddy. We've been discussing for better than a year that we should do a Hangout sometime, and you know, we're regulars on Skype with each other, and we say, yeah, we should do one. So we've elected to do one today. I would think it's kind of launched because of the recent discussions about organic chemistry and specifically about the solubility of DNA. There's been, I mean, to try to prepare the audience for what it is we're about to talk about, I would have to basically post like 7 links to 7 different threads. It's just like a smattering of shotgun discussion all over Google+. It's interesting stuff, and I think it's a chance for people to learn. I would hope that you know, we could talk about that a little bit and try to see where maybe that conversation's gone wrong. And then, you know, maybe this doesn't need to be yet another Hangout. I mean, I think most people who would be watching this Hangout would have been following that discussion and your discussion, Ronnie, with Fiona, and I think you had one with Sam recently as well, Sam Scientist. But I think we should just let her go where it goes, because maybe we want to talk about other features of the conversation and sort of like, what are we talking about, and sort of why are we talking about this? So what do you think, Ronnie? How are you doing today?
I'm doing all right, man. Doing great. Yeah, I mean, I think that there's a lot of things that we could talk about just with the issue of that I brought up with Fiona, for example, because the issue by itself, speaking about as to whether or not DNA is water soluble, is not just an issue of DNA just being soluble. There are implications that we that tend to scatter, such as, you know, abiogenesis and so forth. So. So this could lead on to, of course, a very, very long discussion with theology or philosophical interpretations of what this may implicate.
Yeah, and while it can't be a long discussion about that, because I think we're sort of committing ourselves to sticking with an hour. Nobody ever starts on time and nobody ever finishes on time. But I do hope that it does lead on to another discussion, because I got to tell you, let me just really quick. I want you to sort of introduce us to what the topic is that's going on here. But I want to say, sort of as prefacing to you introducing it, that first off, my fascination with chemistry is mediocre. Like, I had to take it, you know, and it took a lot of it, and I think there were parts of it where I sort of succeeded through memorization, and then when I didn't really apply that knowledge, I don't necessarily remember all those things. So I want to say with some sort of humbleness that I remember a lot of the principles, but there's, you know, there'll be moments when you and I talk about chemistry where I go, oh yeah, is that how that? Oh yeah, well, let's look that up to be sure, or whatever else. I'm interested in this discussion that you've been having with people, because I am interested in it as a component of your overall argument. It's an element of a construction of an argument that you're putting forward. And so what I want to say is, somebody who's, I'll say, generally knowledgeable about chemistry, but not interested as much as I should have been when I was going to school, but is more of a, let's say, at a layman's level of interest in chemistry, but enthusiasm for the topics we're having here. I find that when people are talking with you and you have these exchanges in Google Plus and the messages, that it's like so many of us, like, I mean, not you and not Sam and not Fiona, the rest of the world is looking at that discussion going, okay, but what exactly is the point? There's a great post a couple days ago somebody put up that said, okay, so how does the solubility of DNA affect the reality of there being a God or not being a God and Jesus dying for your sins? You know, and so I hope that we can talk about the solubility thing a little bit, but as you say, I hope that it does sort of branch out a little more to what's the point of all this? Where do you want to start us?
Well, I'd say that the point of solubility, that would have to do with abiogenesis, maybe an ocean foam or whatever, or a prebiotic ocean that was consisting of free-floating nucleotides or of any sort of pre-RNA. So that's really one of the main reasons why that was brought up. As to whether or not DNA would dissolve in water or break down in water, I don't believe that the point would be specific to that, as in whether it would be true or not. That would discredit my disagreement with abiogenesis. I think there's a lot of problems with abiogenesis independent from that. But I would say this, that intelligent design, if I'm going to argue for intelligent design, versus that of abiogenesis, that would not really, it would have something to do with my Christian beliefs in the aspect of creation, but it wouldn't be an attempt to prove or disprove any specific religion or belief, if you get what I'm saying. So one of the premises of my position of creation, I think that is more so what I'm directing this to, which of course, as an atheist, that is something that you would negate or you would be without.
Okay. Yeah. Well, I think I have to admit I was briefly distracted there because I know one of the things that you just said when you were opening this, you said about the issue of whether or not DNA would dissolve or would break down in water. It's that phrase again. Like it just sounds to me like you use the word dissolve and break down interchangeably, and I just can we get past the dissolve breakdown issue? Because I know that when we get into the discussion, I mean, ultimately, let's say we come to an agreement on whether or not on what DNA does when it's in water. Does it prove God or not prove God, or prove that there is or there couldn't be or there must be or whatever else? But let's try to do it one at a time. So, what's your understanding of this? Like, what does DNA do when it's in water?
What does DNA do? When it's in water? Are you asking me about its solubility or its ability to dissolve?
Well, okay. I'll give you a spec. Yes, I'm asking both of those things, but I'm saying let's not use a vague term like it. I mean, even the term "it breaks down" is a little bit. Well, actually, let me say it this way. I had said in a Hangout recently that when we were using the word dissolve, I try to give people credit for what they mean to say, not what the words actually mean. I want to, when you use a word, I want to understand what you understand that word to mean, because I'm not interested in the words. I'm interested in what your message is, right? So, and I said, like, these guys are like, oh, there's a formal definition of dissolve. And I said, well, it doesn't matter what the formal definition is, because we use the word differently. And I use the example of, oh, my hopes have dissolved. Right. Well, when I say my hopes have dissolved, that doesn't mean my hopes have entered into solution. It means that they've broken down and dissipated. They're dust and they're gone. Now, so what I'm asking about DNA is, go ahead, sir.
Well, I'm just going to say that. Well, I don't think I should respond that because you were about to hit on something with DNA.
Oh yeah, I was going to get to the point with the DNA. So let's say you've got DNA. So let's picture, it's the double helix, and it's a whole bunch of atoms that are interconnected. And there's some free protons and some electrons floating around. Just one moment, and then it goes into water. Now, a number of things can happen. It could stay completely intact, or maybe some electrons will come flying off, or maybe some protons will come flying off, or maybe it'll break apart in the way that it's like the train cars separating off of a train. So the nucleotides actually break free and they become individual nucleotides, but they stay coherent, right, like this. Or it could be that the nucleotides themselves also break apart into individual atoms. Or it might even be the case that the atoms break apart into subatomic particles in some big nuclear explosion. I don't think either of us believe that DNA actually goes nuclear when you put it in water. But that's what I'm asking. When you say that it breaks down in water, to what extent does it break down? Does it shed some subatomic particles? Does it shed some nuclei? Does it break into subunits that tend to float around but stay intact? Or do those things break up? To what extent does it break down?
Well, I'd say that it would be affecting the hydrogen bond, right? Because if the hydrogen bond is what's dealing with this in DNA, then with the strands is going to run it unstable.
Okay, so actually, sorry, there's another set of bonds there, I guess. When you think, okay, what DNA is made out of, there's the chains, but then the two chains are interconnected. So there's a connections between the two sides of the DNA chain, and then those might separate. There are circumstances those might separate, but then once you have one of those strands, so there's the connections between the strands. There's the connections within a strand that is interconnecting the nucleotides, and then within each nucleotide, it's got the sugar group, the phosphate group, and the actual whatever it's called, is it not nucleoside?
I'd say this: that when DNA is broken down, it's still going to stay in its heterocyclic base or the purine base. It's not going to be completely broken down into atoms like with sodium chloride, because Fiona just put up a video as well that was breaking this down. The dispute isn't that different bonds or different chemicals are going to break down differently, because in ionic compounds, you'll have a partial negative charge of the oxygen and a positive ion with a partial negative positive charge. And when you bring that with the hydrogen breaking into the sodium chloride apart, that causes it to freely move, and you have free moving ions basically. So you're breaking apart the chlorine and the sodium. With DNA, it's not the same thing. It's breaking down. Both of them are breaking down, but they're breaking apart differently.
Okay, then to what extent is the DNA broken down? Like, do the strands separate? Do the nucleotides come off the polymer?
Well, I would say that it would be breaking down in segments. It wouldn't be breaking down in the same, like I just said, it wouldn't be breaking down in the same sense as sodium chloride would be breaking down, or an ionic bond would be breaking down, but it would be breaking down nonetheless. Because that was mainly the main contention between myself and Fiona, that at first, as far as I was gathering from her, was that, well, no, it doesn't break down. You can actually leave it in water and it would be perfectly fine. I think at one point she said that she's actually left DNA in water for long periods of time and it was fine. Mm-hmm. Well, as far as my reading has gone, and pretty much as far as I've seen all of the sources she's given me, it appears that DNA, if left in water, it will dissolve if left unintended. So the main key word here is breaking down. What I'm concerned with is,
well, again, I'm sorry, you just said if it's left unattended in water, it will dissolve.
Yes.
But I think what. Okay, so what do you mean dissolve in that sense? Because I think if you put DNA in water, it will dissolve, whether it's attended or unattended or whatever else. As soon as DNA gets wet, it enters into solution, right? It doesn't. I mean, as opposed to if you had a brick of lead and you dropped it in water, it will not enter into solution. It won't dissolve. It'll retain its complete like macro structure.
Yeah,
DNA, as soon as you put it in, it'll dissolve in water. But you mean it'll break down over time in water? Is that what you mean?
No, well, if you take something that's got too strong of bonds, of course, it's not going to be breaking down. But different effects will happen when something is dissolving. Like if you put it in a solution means that you have a solute and your liquid as well that you're going to be using right there. When you put DNA in solution, like an aqueous solution, you're not putting it in a solution by itself. You're putting it in the solution with salts and with other things as well, like ethanol. So I think that when she was saying, well, it goes into a solution, I think that she is missing that when you're putting it in a solution, you're putting it in with other things as well.
Well, I think that's partly where your discussion with Fiona. There's a couple of things I would refer to as missed opportunities. One of them was I'd mentioned earlier today about the acetic acid, but let's not go off too far on that. Was the very specific discussion of okay, you just used the words, when she puts DNA into solution. She entered into a very sort of detail focused discussion about the process of extracting DNA in the laboratory. And so you're right. I heard her say a number of times that there are salts you use, there's surfactants or detergents or something to break apart the cells, and then there's salts and there's ethanol and there's a whole process like that she'd laid out. And then apparently since that time, and I haven't seen them, I've just sort of glanced at them, but she's even posted like instructions on how these things are done. But a moment ago you said to me, you said, well, when you put DNA in water, you would use these salts and this ethanol. And my correction would be, well, I don't. Fiona does, but I keep my DNA in aqueous solution in my own cells without adding ethanol in great quantities or great frequency occasionally. But were you laughing at that? Because it wasn't that funny. Okay. I was generous of you. But the laboratory process for extracting DNA involves ethanol and these stabilizing salts and whatnot. But all I'm saying is, what happens when you put DNA in water? I'm saying yes, it would dissolve. But by that, I don't mean that the DNA would break apart in the same way that a person's hopes would dissolve. I'm saying that it would enter into solution. In doing so, I believe it gives up some protons. It would actually lose some nuclei, but the structure would remain intact. And that's why I'm asking you. Well, okay, let me just straight up ask the question again, so that we're not talking about it's not the laboratory process. What happens if I had, if I filled this thing full of DNA and I poured the DNA into a bucket of water all I've got is DNA and I've got water and I dump it in. What happens to the DNA? Does it dissolve? Does it break apart? Decompose? Like, what does it do?
Well, I think that it would dissolve. It would break down. That's what it would do. That's what it means to be water soluble. It would break down. It would dissolve.
Okay. Well, you use the word dissolve, breakdown, dissolve. You use those again. I don't know. You're using them interchangeably. Okay. If you say it breaks down, to what extent does it break down? Does it break down until like do the strands separate? Does it break down until like what's the term for it? So polypeptide, oligopeptide. Oh, listen to me. Nephilim Free made that mistake a few years ago, and people still haven't stopped teasing about it. I meant polynucleotide. It's not a polypeptide. That's funny. Does it break down into a polynucleotide, oligonucleotide? That is, you've got a whole bunch of nucleotides in a chain. Does it break down into like here's 10 here and 15 there and 4 there? Or does it break down into individual nucleotides? Or does it stay intact, or does it split in half? Like to what extent does it break down? It got real quiet. Are you still with me? Can you hear me at all, or? Oh, one wonders. I heard all I heard through the headphones was you drew a breath, and it sounded like you were going to answer, and then now it's eerily quiet. We still can't hear you, Ronnie. If you are talking, we can't hear you. Feeling the urge to fill what is now dead air, I'll say. I think the context I'm trying to frame this in here is that there's multiple bonds in DNA, right? There's all the internal organic bonds amongst the things that make up a nucleotide, right? That can be considered sort of a blob, like a train car, and then they click onto another train car and on another train car, and that gives you your nucleotide sequence. And then there's the bonds between the nucleotides within a sequence, within a strand, and then there's the bonds from strand to strand, the A being attracted to T and the C and the G. And off he goes. Oh, the internet. My son, who's 6, by the way, had a thing at school about safety on the internet and how to avoid predators and stuff. And we're on the drive home, and he asked me, "So what is the internet?" And that was a weird question. It's really hard to explain to somebody who's throughout their entire life there's been an internet, you know, and try to explain, well, computers are all connected, because of course they're connected. So how much do I have to babble here before he gets back in? Let me just do the thing that we always do when this happens. Skype. Oh, okay. So he's also off Skype. So apparently it's a just dead as doornail situation on his end. There we are.
Yeah, I'm sorry about that, man. I don't know why my browser keeps force closing on that like that.
Oh, yeah. Well, just let you know where we what it was. I asked you a question about to what extent the DNA breaks down, and then the last we heard, you kind of drew a breath to answer, and then literally no words came out. So whatever it is you had given as an answer, you can't even sort of pick up where you left off because we didn't hear any of it. So for clarity, I'll repeat what the question is. I'm saying there's different bonds in the DNA. So starting right from the nucleotide, there's a whole bunch of organic bonds in amongst those atoms that form this nucleotide, which I'm sort of using my hand as a blob to say, here's your stuff. But then the nucleotides are bonded to each other within a strand, and that's sort of the train cars coupling together, this one to the next one to the next one to the next one. And I remember something about 3' and 5' ends, and the 3' of one clicks onto the 5' of the other, like train cars. There's an obvious front and a back to these things, and it makes a sequence. And then the third type of connection, bonding, would be the bonds between the strands. So the A and the T are, oops, I should do it with 2 fingers, shouldn't I? I forgot the backwards. Yeah, the A and the T have bonds across the strands. That's the gap in the strands. And then the C and the G have bonds as well. So those are I'm just loosely, those are the 3 main types of bonds within the nucleotide between the nucleotides within a strand, and then between the two strands. So when you say the DNA breaks down in water, which bonds are you thinking of here that breaks down?
But did you just mention the phosphodiester bond?
Phosphodiester bond. I may have. I don't know. Again, this so many years ago for me. I mean, I would. You know what I should do to not sound so dumb? I'm going to pull up the wiki page and look at the diagram of what a nucleotide is.
Mm-hmm.
That's why at the beginning I expressed my tremendous disinterest in.
So I'm just asking you because it sounded like that's what you were.
Well, you just tell me while I'm pulling up the picture. What was I looking up? Nucleotide. Which is the phosphodiester bond? Is that the one that's the backbone? That's what joins the nucleotides together. Is that right?
Mm-hmm. Yeah.
Yeah. Into the chain, right? So I'm using that as my analogy of you've got train cars that within each train car, there's bonds that hold the wheels onto the truck and the bin onto the deck, that sort of thing. And then there's the connections between the train cars. So in this example, it's the what's the bond that interconnects the train cars, the nucleotides?
Well, yeah.
The phosphodiester bond.
Yeah, well, of course, I think that would be what it is because that's where the polyanion is in DNA, right? So, of course, if the sugar phosphate molecule is what's holding together these base pairs, then when that breaks apart, that's how it's going to fall apart. It's going to break everything apart that way.
Okay. Yeah. Then I think we're on the same page with that now. Yeah. So you're saying the phosphodiester bond is the one that couples the nucleotides together, and you're saying when you say it breaks down, then I wonder, do you mean it breaks down? So you got a whole bunch of these things. Well, however long the DNA chunk is you have, there may be. Let's just pick a random chunk of 1,000 nucleotides on one side of a strand. Does it break down into 1,000 individual, like do all those phosphodiester bonds break down into 1,000 individual nucleotides now floating around freely? Or does it say some of them intermittently break down so that you have, and the word I was trying to use before was oligo, meaning short chain. Oligo, this would be an oligonucleotide sequence. So you have 10 nucleotides still stuck together. You had 1,000, but now broken into little pieces where you got 10 here and 4 there, and 8 over here. To what extent is it breaking down?
Well, I can't really specify how much DNA would be breaking down. I mean, it would depend on whether or not it's diploid or octoid, or you can't put a number on that from off the top of my head. We know that DNA is very complex, and there can be all sorts of different amounts of whatever sequences or nucleotides in DNA in whatever experiment. So
okay,
there's no way for me to put a number on how many would be breaking down.
Okay, yeah, sorry. I think I made it sound like I was trying to pin you down on a specific number so that you were going to tell me it's 18. It's going to break into pieces 18 long, and that's not what I'm looking for. I'm saying, is it going to break down into completely into individual nucleotides, like every one of these phosphodiester bonds, that is the coupling between the train cars, every one of them is going to break down and you just got a pool of nucleotides floating around? Or is it the case that some of them would break so you'd have chunks? And I think what you're saying is more likely you'd have chunks. Maybe over time they'd all break down. But in either case, the fact that you'd say that any of them, go ahead, sorry.
Well, I was going to say that you would agree that DNA is a weak acid.
Yeah.
Well, weak acids, I believe that they disassociate at a different rate than some of the stronger acids would. So I would say that it would depend, I believe, like, for example, like if you were to take salt and you were to take sugar or any sort of soluble substance and put it inside of water, it wouldn't automatically dissipate as soon as you were to put it inside of water, right? You'd shake it up and some dissolve at a faster rate than others. And if you put too much, and the equilibrium is off, well, the residues will actually fall to the bottom of the glass. So I think that this might be something that we'll be facing as well with DNA.
But when you now mention, as you have before, that you use the term about acids disassociating, right? So you take something that is an acidic compound, meaning it's a ready proton donor, and you put it in water. It will, in equilibrium, dissociate, right? It will break into pieces. But the question is, what are those pieces? So the post I made today which in 10-point font is as long as my arm. So I'm going to, and it was also like post number 80 on a very long thread. So I'm assuming most of the viewers hadn't seen it. But I was trying to make the point about what happens when these compounds get into water, specifically acids. When they get into water, what level of dissociation happens? And I was using the example, and in part motivated by Fiona, because she raised this, and I kind of wish that you guys would have pursued this. What happens when you take an organic acid that's more simple and more familiar? Like, let's take acetic acid, classic vinegar. It dissociates in the sense that you've got your the acetate group, and at the end of it, there's a. I was actually going to open one of those doodle sketch things so I could screen share, and we could draw out the C double bond O bond OH, instead of me going like this with my fingers and saying, pretend this is the carbon, and then this is the double bond to the oxygen, and down here is your hydroxyl group. Well, down here at the hydroxyl group, there's the oxygen and the hydrogen don't have a really fair sharing of the electrons, and the oxygen being a little more sort of greedy with its share of the electron time or the electron density. And I remember I had a chemistry teacher once tell me that you got to think about covalent bonds being like a marriage. It's not just these things are in solution, but these atoms are sort of married to each other. And it's a helpful analogy a little bit, except for the fact when you start thinking, okay, now carbon's allowed to be married to 4 other atoms, like what? And you can be double married to someone. But in any case, when you've got that relationship where the oxygen here and the hydrogen are having an imbalanced marriage, where the oxygen tends to hold on to the negative charge a little more, that electron cloud a little more, that leaves the hydrogen slightly positively charged, allowing for attraction to some other oxygen in a totally different molecule. But it also means that hydrogen might feel a little bit left out in the relationship and will be inclined to just leave and say, fine, you could keep my electron, and it just goes ahead and it wanders off and joins up with a water molecule, for example. So with something like acetic acid, you've got your acetate group, and with that proton that sort of isn't really happy in the relationship, and it'll wander off. So when we talk about the dissociation of acetic acid, as soon as you put acetic acid into a sufficient quantity of water, it will, in equilibrium, and a very aggressive rightward equilibrium, it'll dissociate. But the dissociation is the launching of that free, unsatisfied proton, right? It's not the dissociation of all the other constituents. It's the carbon-carbon bond doesn't break. The other carbon-hydrogen bonds don't break. So to get back to DNA, when you ask me if I agree that it's a weak acid, what I think happens is you've got all these train cars, and each of the train cars in the phosphate group has one of these OH, these hydroxyl groups, and those hydrogens have an imbalanced proton or electron sharing with the oxygen, and those hydrogens will dissociate. They will wander off. But my understanding is there's no dissociation of the nucleotides. They stay together. So I apologize for the length of that response, but I just wanted to make clear that my understanding, when you ask me if something is a weak acid, and in this case an organic acid, when it goes into water, its dissociation that happens is the liberty of these protons. Like one single nucleus, literally one proton, will wander off of it and go do something else. But the actual structure of the DNA is all still there. Is that goofy?
Well, no. Well, I think, are you trying to tell me about the asymmetrical electrical distribution in the molecule around the molecule, and that affects as to whether or not it's polar or nonpolar?
Well, that component of it, yeah, I think we're talking about the same thing there. Is that the asymmetrical distribution, and not around the whole molecule, but specifically around the hydroxyl group. In the case of something like acetic acid, which, you know, the DNA is this big, acetic acid is only about that big, and so there's 2 carbons, and one of those carbons is attached to a double bonded to an oxygen, another one is double bonded to a hydroxyl group. I may have the wrong formula. That is acetic acid, yeah, COOH. Where the one carbon's bonded to the hydroxyl group, that is an O and an H, there's an imbalance of charge just in that one little wing there on the hydroxyl group, on that one. But there's only 2 carbons in it. The whole molecule, if it's only that long, the imbalance of charge is that long, so it covers a significant distance on the thing. Whereas if it was a longer chain, if you had something like 10 carbons, each populated with hydrogens. And then the carbon on the very end had an OH group, a hydroxyl group. There would be an imbalance of charge, a polar segment of it, just at the very, very end of it. And that's why when you talk about DNA, it's very, very small parts of it where you have this one proton that is disinterested in staying in the family, and it will wander off.
Well, the problem is that where the polyanion is on the DNA, that's on the sugar phosphate backbone. So the sugar phosphate backbone, if you screw around with that, that's going to render it unstable. So I think that's the difference here. Where the polyanion is on the DNA, that is what is going to affect the whole strand, both strands of DNA. So I think that would be the difference between what you're saying.
Okay, so you say I'm going to agree with you there that since the portion that I'm talking about, the net phosphate group, if it were the case that you messed with that connection, maybe that release of the proton, that is, it's an acid, it's a proton donor. Maybe that would be the example of like how train cars are very tightly coupled together, but all you have to do is pull a pin out. Actually, that's not true. People haven't used pins for years. Tractors, they use the pin. There's a tongue and then the thing like this and a pin. Is that no matter how tight that thing is, all you have to do is pull the pin out, and now it disconnects, it uncouples. And is it the case that this proton coming off in solution is the thing that would break apart the the phosphodiester bond and liberate whole nucleotides? Is that what you're suggesting?
Yeah, well, that's pretty much what I'm suggesting. If this is dependent on the stability of the strand, and that is what's screwed up, then it's going to be unstable. So if you affect the polyanion in DNA, then that's basically what's going to happen.
Yeah, well then at that point, that's where I wouldn't agree with you, because this phosphate group, it's a terminal group, right? Not the phosphate. The hydroxyl group on the phosphate segment of the nucleotide is a terminal thing. So all it is you've got a little bit of a negative charge around that one oxygen that's sort of off to the side, and then, well, the proton leaves without taking its own electron with it, so it leaves that as a negative charge at that oxygen. But the connection's back up here, and there's other covalent bonds that are back there. So just the liberation of that proton, it was already an imbalanced charge. There's that polar property there on the hydroxyl group, and all it is it just becomes slightly more polar. But
yeah, but its polarity, I think, is the of importance here. See, we're talking about something that's polar. We're talking about something that would have that would be affected by the H2O in the water with the partial positive charge in the hydrogen and the positive ions, I believe. So when this is affecting the DNA strand, the polyanion, this is it's gonna tear it apart. It's gonna start to break it down.
Okay. Well, there's one of the difference in the analogy here. This is why analogies are helpful only as far as they're helpful, because again, my understanding is that hydroxyl group, this sort of sticking off the side of the phosphate group, is not part of the bond with the sugar, right? That those other bonds are there, and with the train car example, or I used the tractor pulling a wagon or whatever, these physical things you can pull apart and separate and whatnot, and there doesn't need to be anything left in that opening. But in a decomposition reaction, that is, you have some compound and it goes through some reaction, and then it's now two different, a single reactant generates two products. There has to be something in there to fill those ends. So for example, the hydrolytic reactions. There are many polymers where you when they say it's hydrolytic, they say that it's water breaks the thing down, but it's not really what it is. It actually consumes water. So you might have some large organic molecule, and then when it breaks down, there's a water molecule nearby, and one proton from the water molecule goes and tacks onto the end of this, and then the OH from the water molecule goes on and forms a hydroxyl group on the other one. And then the catalytic reaction, where the two things join up again, they do so by forming that bond and releasing the hydrogen and releasing the hydroxyl group, which then join up and form a water molecule. It's actually it's not the presence of water that sort of causes the thing to break apart. The water itself actually lends the end caps that help close off those two things so they can go in their separate way. So what I'm asking is in that context, how would you describe, like, when the phosphodiester bonds break so that the two nucleotides go apart? What's the reaction? What is the substitution that goes to cap those things off? Free radicals.
I'm sorry, can you hear me, man?
Yeah.
I was fiddling around with my mic while you were talking. I apologize. It came undone. I got two mics on my the one on my camera, and I got one on my Blue Yeti microphone, and both of them came undone. So I couldn't find the cord to see which one it was when I tried to plug it back in. So can you repeat what you just said? I apologize.
Sufficiently distracting for my. Yeah, I'm just wondering, because I mean the and maybe we might want to just sort of well, okay. What I'm saying is that when you break apart a bond in a polymer, it doesn't just pull apart like train cars, right? There needs to be a substitution. There needs to be something else go in. Otherwise, you just have a free radical there, right? You can't. Let's go back to the acetic acid example. So in the middle of acetic acid, you've got a carbon and a carbon. This one's populated with hydrogens. This one's got the hydroxyl group, and you can't just pull apart the two carbons, right? Because carbon enters into 4 covalent bonds. If those two carbons weren't stuck to each other, now this needs something in it, right? Or it's a free radical, right? And so would this other one. And I was using the example of a hydrolytic reaction, where sometimes in the presence of water, you'll take a proton and stick it on this one. You'll take the OH minus and put it on here, and it becomes a hydroxyl group. I'm saying, so that's why I'm saying I don't think it's a sufficient description to say, well, if you destabilize the charge over here, you create a bigger charge on the hydroxyl group, then that would sort of break apart.
Well, like hydrofluoric acid, right? Hydrofluoric acid, it's a weak acid. And you have a hydrogen ion that will dissociate, and what you'll have left over is a fluoride anion. But you can reverse that after the effect is done, and you'll have hydrofluoric acid again, right? So I think that what you're saying is that, correct me if I'm wrong, is that it would still maintain being DNA, right?
Yeah, I'm saying.
But the problem is that with acids like that, when you're exchanging protons or ions like that, or whatever, what ends up happening is that it changes its molecular structure as well. So it's not the same thing that it was before. It also affects the water around it as well.
Yeah, well, my understanding is that to whatever extent it changes, it's a really, really small extent. It's simply, you've got exactly the same. You could draw out the DNA molecule, all the little lines and everything. It's just at the end of the hydroxyl group on the phosphate group, the H has popped off, and you want to put an O minus instead of OH there. But the molecular structure, when you sort of step back and look at it, it's still exactly the same thing. I mean, I could ask you this way, let's forget the imbalanced electron sharing. What effect does a polar solvent like water? What effect does a polar solvent have on sorry, these are covalent. What effect does a polar solvent have on covalent bonds?
What effects does a polar solvent have on covalent bonds?
Yeah.
Like, can you specify that? Because there are different types of covalent bonds.
Well, I guess, I mean, if you have to break it down that way and say, well, for example, in a balanced electron sharing covalent bond, it does nothing, but in an imbalanced one like the hydroxyl group, it does this or does that. However you need to break it down to answer that.
You're asking me what it would have, what effect it would have on a covalent bond. So which specific type of covalent bond, like, I just need a little bit more elaboration on your question.
Well, like examples, or I guess like any of the covalent bonds. Like say if you put octane, right? Octane has a lot of carbon to carbon to carbon to carbon covalent bonding. So the carbon to carbon bond, or it's something like cyanide, the carbon to nitrogen bond, which I think in cyanide is a triple bond even. Any of those bonds, or I mean, I guess why don't we get right to it? I mean, the specific thing is what we're talking about is the phosphodiester bonds between. I mean, those are covalent bonds, right? The phosphodiester bonds that are like the coupling of the train cars. What effect does a polar solvent have on those bonds?
Well, this is the reason why I'm having like trouble with the question, because we're pretty much talking about the effect that it would have on DNA. Like that's like the context of the discussion. So of course, the effect that a polar water would have on a covalent bond like DNA, a soluble DNA, would be that it would be soluble. It would break down. So when we got into the sugar phosphate backbone and how it would break down, so that would be the effect of what it would have on DNA.
Yeah. Well, I'll tell you where. So once again, you just said it would be soluble. It would break down, and I don't know what to say. I just see these threads go by where so many people tell you that solvation and breaking down, that is decomposition. Like,
well, can I? The reason why I'm bringing it up is because I think that breaking down is pretty much the biggest disagreement here. And when they disagree with me, I see that they're showing videos or they're showing material that sort of falls in line exactly with what I'm saying. Fiona put up on the source that she showed, for example, on her podcast or her hangout that she held after we held ours. It said specifically when you're doing this alternative type of solution, when you're trying to deal with DNA, to be careful when using water, because it would deteriorate DNA. So I'd like to share, because she actually found a really good video, which was better than the one that I actually used, because the video that I used only had to do with sodium chloride. Can I screen share that right now so that we can look at the language?
I actually didn't see her hangout. I did see your conversation with her, but I didn't see her hangout, so I don't know about that second video you're referring to. And yeah, go ahead and load up the screen share, and I'll do the whatever called present.
Okay.
Present to everybody. But I just want to say, I mean, my understanding is that the polar solvents don't break down covalent bonds, right? They don't actually sever those bonds. This like dissolves like, I think is the phrase they use.
Give me 1 second. I'm trying to find it.
Well, that's why, I mean, as you're doing that, I'll just fill you out here. But that's why I was trying to make the point in that post this morning that like you can have something like sodium chloride, which is all ionic bonds, and they pack together in a crystal, like a checkerboard pattern, alternating sodium chloride, sodium chlorine, sodium chlorine, and then in the when they're put in water, then the nuclei wander away. Each nucleus taking with it some number of electrons, not the right number. The chlorine tends to leave take an extra one with it, and therefore it's chloride, the chlorine ion, and the sodium tends to walk away one electron short. But they're free to move about in solution and interact with the water molecules, so that those bonds actually get broken. But then the example that this guy, Daryl Soar, I think his name was, had found this video where the guy explained that if you put sugar in water, there's no change in the nuclei. That you could draw a sketch of these nuclei, and you put them in the solution, and in solution, the same nuclei are in the same arrangement. There's no molecular level change with it when it's in solution. And I was saying neither one of those examples are real helpful or relevant to DNA, because DNA is closer to something like acetic acid, where there's a big part of it that stays exactly the same, and then one nucleus wanders off. That nucleus specifically is a single proton, a hydrogen ion, that leaves the molecular structure, abandoning its electron, leaving a negative charge here and wandering away as a positive charge. And I just think that's a better example for explaining what DNA does. You got a big blob of stuff here, a protein that's like, oh, you're not fairly sharing your electrons with me, so and it leaves and abandons its own protein, electron. Yeah, you got your screen share loaded up there. I'm just going to keep mixing up words until you get your protein, proton. I mean, electron. Okay. So
All right,
I'm going to present to everyone and go ahead and let her rip.
Okay, do you see what I'm showing?
Yeah, I see the Hall of Mirrors effect here. So, okay,
it seems she removed it on her Google Plus page, but I found it through my history. Give me 1 second.
Use toys more efficiently while reducing our carbon footprint.
What happens when stuff dissolves? I mean, like,
this guy.
To the atoms and molecules that make it up. I want to talk about two things here that you dissolve all the time: salt and sugar.
Can you pause it for just 1 second, Ronnie?
Like what kind of what?
I just want to say, and this is a really good. This is the one that Daryl's I forgot the guy's name. That's so bad of me. It was just such a good find. This is the video that he found that Fiona, he shared it, and then Fiona had reshared it, and I commented on it, and that was the one where I made that really long comment. And one thing I was a little puzzled by is that what he's calling sugar there, it's what is it? It's a C2H4O2. I'm trying to read there.
I believe it's 2 carbons, 4 hydrogens, 2 oxygens.
Yeah, that could be anything. I mean, acetic acid, vinegar has that. I don't like that as a nomenclature system because it doesn't tell you how they're organized. I think there's about 18 different compounds that have that same. I'm probably exaggerating, probably not that many, but then if you look above it, he's got the little 2 green dots, or the 2 carbons, and then one of the carbons has an oxygen, the other one has an presumably that's a double bond. But in that orientation, that's glycoaldehyde. I don't think that's really a sugar, but I still think his point is made. I'm not saying he's wrong about this, but I just found this a really odd video to say, like, oh, here's how sugar dissolves, when the example he's giving is actually a glycoaldehyde and not a true sugar. But I don't think that detracts from your point. I just want to say this is the video I'd seen, and I think it helps illustrate it. So why don't you go ahead and play it and then tell me what.
Well, I think what he's trying to do is try to draw the distinction between ionic and covalent reactions with
sure.
water, polar soluble,
Sure. I just don't want the audience to be confused and think that when he says he's on the side, when he says salt, he doesn't mean just any old salt. He does mean table salt. And then on the other side, he says sugar, and he certainly does not mean table sugar. That's glycoaldehyde, which I don't even think is a sugar. Maybe it is. Whatever. Who cares? I'm sorry, Ronnie. Go ahead and play it.
Okay.
White powders made up of little grains, and you could pour both of them into water and stir around, and you see the grains get smaller and smaller, maybe break apart, until eventually they've totally disappeared. They've completely dissolved in the water. That's what you see with the naked eye. But if you had atomic vision and you could see the atoms that make up salt and sugar, what would it look like as these grains broke apart and became invisible? That's what we're going to talk about here. So it actually,
I want people to pay attention to the language that he's using, though, breaking apart, because it seems like the word dissolving and water is where people are trying to get out of my case, but it becomes a semantical issue. It seems like everywhere we look, the same terminology, right down to the fundamental reactions in chemistry, breaking down is the specific terminology used when talking about this. I just wanted to point that out.
Okay, sure, yeah.
Actually depends whether something is an ionic or a covalent compound. It depends on what it would look like when it dissolves. So over here we have salt, and this is an ionic compound. This is what a grain of salt would look like, and it's made of sodium ions, Na+, which are metals, and Cl, chloride ions, these blue things here, which are nonmetals. So salt is an ionic compound made of metals and nonmetals. Sugar, on the other hand, is a covalent compound because it's made of nonmetals, carbon, oxygen, and hydrogen. And these nonmetal atoms are connected together into a molecule. So a grain of sugar would look like this. It would be a bunch of these sugar molecules all kind of lumped together. Notice that a grain of sugar is a lot more messy. It's not nearly as well organized as an ionic compound, this grain of salt over here. Anyway, let's look at what would happen when we dissolve these. We'll take a grain of salt, dip it in the water, and start stirring around. With our atomic vision, we're going to see that the atoms that make up this salt are going to come apart from each other. They're going to break apart, and they're all going to start floating around in the water individually. This is what it looks like when salt dissolves. Okay. Now let's take our sugar. Here's our grain of sugar. It goes in the water, we stir it around, and the grain of sugar is going to break up like we saw the grain of salt break up, but it's going to break up in a different way. It's going to break up into the individual molecules that made it up. But these molecules are not going to break up into the individual atoms. They're going to stay as molecules, and those molecules are going to start floating around in the water. A big mistake that people make, I don't want you to make this mistake, is they think that when sugar or other covalent compounds dissolve, they think that the atoms that make up the molecules totally break apart. And then you end up with a glass of water that has all these carbon and oxygen and hydrogen atoms just floating around. That does not happen. Big red X. Instead, the molecules stay together. Well, the atoms in the molecules stay together. So this is a big difference between how covalent compounds dissolve, where the molecules stay molecules, and how ionic compounds dissolve, where the grains of these things like salt actually break apart into the individual atoms. So,
can you pause it there?
What does it look like when something dissolves in water? The short answer is, it actually really depends whether you're talking about an ionic compound or a covalent compound. If it's an ionic compound, it's going to break apart into all of the individual atoms. But if it's a covalent compound, the clump of the molecules will break apart into individual molecules once it dissolves. But the molecules themselves will not break apart into atoms. They will stay as molecules dissolved in the water.
Okay, that's good. Can you go back, just put your playhead back like 10 or 15 seconds or something so that that image is up where he was showing the two. Yeah, just click there and pause it.
Like this?
Yeah. Now, the thing that, again, I thought this was a really helpful video. Again, I don't think it's a perfectly helpful comparison because it doesn't address what happens with DNA, because there is some dissociation with DNA, and that is the hydrogen nucleus popping off of the phosphate group. Now, notice that if you look up in the upper left corner where he shows orange dot blue or orange blue, orange blue, orange blue, there can be two, a sodium and a chlorine that are side by side, but then once it's put into solution, they completely dissociate and they're just random. Now, when you let that water evaporate, they're going to form new crystals, and they might not sort of reappear in the same order. There's going to form that lattice work again, but it's going to be a different jumbling of them. Turns out not to matter one little bit, because one sodium is as good as the next, right? But on the other side, where he's got, say, the two green dots that are touching, those two carbons are always, below that he's got, there's two green dots on that molecule, two green dots on that molecule, two green dots on that molecule. Those two carbons are always bonded together. Nothing about putting it in solution breaks apart those carbons. And that's my understanding of what happens with the with DNA when you put it in. The water doesn't affect the phosphodiester bonds that keep the nucleotides together. All it does is it pops off that hydrogen, just like with vinegar, but it doesn't break apart the phosphodiester bonds that hold the groups together. And just real quick, the reason why this happens. I mean, Ronnie, do you know the reason why sugar sticks together as a solid?
I'm sorry?
Do you know the reason why sugar sticks together as a solid, and then why it so easily breaks apart into individual molecules in water?
Well, because it's a covalent bond. When it's What they're basically trying to talk about is when the sugar breaks down as a molecule, it's going to be breaking down into constituent different molecules. It's not going to break down to different types of atoms or different types of structures like in salts.
Right.
But I would say that the problem being is that even if the carbons are do you still need this up too?
Yeah, kind of. No, it's okay. It's okay. We can go with that.
I would say that even if the carbons are still attached, and the oxygens are still attached, affecting the hydrogen will affect the molecular structure of DNA as well. Well,
Okay.
not DNA, but the sugar that they were showing as well.
Here's the big difference, and this is the part of the Hangout I'd like to sort of bracket off and put a big asterisk around to say, like, okay, here's the thing that's hugely different amongst those examples. So in the salt, okay, when I asked you a second ago, do you know what holds sugar together? So that when you have sugar in the sugar bowl in your kitchen, it sticks together into discrete crystals, and they're very tightly packed crystals. So there's got to be bonds holding those molecules together into crystals. So your salt is held together because the sodium and the chlorine are tightly packed, right? Until you put them in water, and then the chlorine wanders away, carrying off an extra electron. But what is it that holds sugar together? When I asked you that, the reason is I'm asking you, it's as opposed to something like methane. If you had a jar full of methane in your kitchen, in 10 seconds, you're not going to have a jar full of methane because the methane just wanders off and buggers off and does its own thing. Those molecules don't bind together. Why do sugar molecules bind? The reason is there's a bond, an intermolecular bond between sugar molecules. Sugar is actually attracted to other sugars. So we have covalent bonds that are very tight within an organic molecule. We have ionic bonds, which can be tight under some conditions, but it's based on this.
Well, the problem is that, of course, there are intermolecular bonds as well within carbon as well. So I don't really see not carbon. I'm sorry, sodium chloride.
Well, yeah, okay. But
and you really got to pay attention to the fact as well before we move on to something else that those intermolecular bonds are, of course, altered by the interaction of water.
Right. Well, that's what I was getting at with with sugar. There's always going to be this hydroxyl group with this imbalanced sharing, so that the hydrogen is sort of mistreated in the way that it doesn't really get its fair share of electron time. It's sort of like a marriage where one person in the marriage sort of keeps more of the money than the other one. They're sort of responsible for the finances, and they sort of drip and drab the money out to the other one, and then finally that one just goes, "Oh, fine, be that way," and then they leave the kids. Right? It's just a helpful analogy I got in high school, although it's very quickly problematic. But so what that does is it leaves, because of that imbalance, it leaves a very slightly polar charge there. So that hydrogen of that hydroxyl group is slightly positive, and the oxygen on the hydroxyl group of another molecule is going to be slightly negative. So that hydrogen would be attracted to that oxygen, and that's those intermolecular bonds are very weak. It's enough to hold sugar together in a crystal when it's dry, but as soon as you get a little bit of water into it, the water itself is polar, right? So now the sugar molecule that has this neglected hydrogen that's slightly negative, it's neglected, slightly negative, insert your own anthropomorphizing there. Normally it would be attracted to the hydroxyl group on another sugar, but now there's all this tantalizing water around, which is polar, and there's that, the butt end of the oxygen sticking out, being somewhat negative. Sorry, I got it backwards. The oxygen is, when I said a moment ago that the disappointed hydrogen proton is slightly negative. It's not. It's positive. It doesn't get enough electron time. I got that backwards. So that's where the analogy isn't helpful. That's why I said that. So let me start again. The hydroxyl group on the sugar has the hydrogen that's attracted to the oxygen part of a hydroxyl group on another sugar. When you introduce water, it has the opportunity to be attracted to the polar nature of the water. So the water very easily breaks apart these relatively weak intermolecular bonds. That's why sugar so easily dissipates into a cup of tea without any change at all to the molecule of the sugar. It's just now that the sugar molecules, instead of sticking to each other, they now have a chance to dance around with the polar water molecules. My point here is that does not happen with DNA, because the phosphodiester bonds that interconnect these train cars are covalent. So the water doesn't go in and interrupt. The fact that the polar water goes into the phosphodiester bonds in between the nucleotides, that doesn't serve to interrupt it. It does with sugar. It'll take a sugar chunk and break off those molecules because they're held together by intermolecular bonds, which are relatively weak. And now, oh, and now I'm attracted to water. Now I'm attracted to water. That doesn't happen with nucleotides. Nucleotides won't break their phosphodiester bonds. They're covalent, balanced covalent phosphodiester bonds for the chance to have some dalliance with water. They will stick together in water.
Well, no, they won't stick together in water, because remember, the hydrogen that is with the or the polyanion in the DNA is what on the sugar phosphate backbone is what is keeping it stable. So if that is what is disrupted, then by the H2O, by the water, then that is going to render it unstable. That is specifically what is going to happen in this covalent bond, this difference covalent bond, which is going to render it unstable. That's the reason why when a sodium cation is brought in between the polyanion and DNA, that it sort of, I don't know how you want to put it, intercepts what would happen with the water. It keeps that from happening. It keeps it from breaking down.
Yeah,
the difference.
Maybe we're
the difference. So I mean, you can't really put it on sugar phosphate, the backbone in DNA, what you would put on with sugar, for example. So I mean, different chemicals, they interact and they change differently, and they have different needs and necessity. Obviously, I mean, we all know and understand that DNA is needed in sequences. You can't disrupt the stability of that sugar phosphate backbone.
Yeah, well, I think we're running the risk now of sort of repeat. I think we do understand each other. I don't hear us arguing, but I also think we're now at the point where we're running the risk of just repeating over and over again. Let me see if you agree with this assessment of how we disagree. And that I'm saying, I swear, Ronnie, there's just no way that the phosphodiester bonds that hold the strands together are that easily interrupted by the presence of water. And you're saying, well, those bonds are destabilized by the ejection of this free proton, the ejection of the hydrogen off the phosphate group. And I'm just saying, no, that doesn't destabilize. Like, covalent bonds are super tight. They don't destabilize by the presence of some polar solvent somewhere nearby, or by the loss of an already somewhat positive hydrogen group, wandering away here. I just think we're at that point in the conversation where I'm saying, look, they don't break down just because a polar solvent like water is around. And you're saying, well, of course, like, once you destabilize it, unless you have something else there, to neutralize that charge or do something else to provide stability, it's just going to fall apart. Does that sound like a fair characterization of where we're missing here?
Well, yeah. Well, I see where we're disconnecting here, but I think that the problem is that, all right, if we're going to be going by the description of what dissolving means, by what chemists are saying, and if the breaking down of covalent bonds it's maintaining being a molecule, breaking down into different molecules, or breaking down in its structure, well, then that's what's happening. So that is specifically what I'm saying, is that DNA, it breaks down because it's soluble in water, and as a covalent bond, it's of course going to be breaking down different than sodium chloride would, or even different acids would. But it would still be breaking down.
Yeah, so, but I'm saying it wouldn't be breaking down at all. It's not breaking down differently.
See,
I'm saying it literally doesn't break down at all.
But I would say, how could you say that? How could you say that it doesn't break down at all?
That's a good
if by the definition of soluble, or the meaning of dissolving, according to what some of these chemists are saying, or even just the video that I just showed right now explains what happens in that process. I mean, because because it all comes down to that to these positive charges, or this polyanion and the backbone of that sugar phosphate molecule. If you disrupt that, then the molecule is going to be rendered unstable and it's going to break down. That's what's holding together these sequences of DNA. So I think the point would be is that if that is disrupted, you know, chemically speaking, factually speaking, if that is disrupted, then it's going to break down.
No, I think it's your point, but I think you're putting a lot of stock into and then taking even more currency out of this idea that I'm agreeing and Fiona's agreeing and everyone else in their dog is agreeing that DNA is soluble in water. If you put DNA into water, it will enter into solution, and you're cashing out of that. Well, what chemists mean when they say dissolve is to break down into its constituent parts, and it just takes us back to the place of no, that's not what we're agreeing to. When we say it dissolves, it simply means that it enters into solution. I actually saw you type that as a criticism of something about Fiona. You said, well, all Fiona could say was that it just enters into solution. That was the most she could say about it. And I'm thinking, well, that's actually what the definition of dissolving is, entering into solution. And that's what DNA does. It enters into solution. It dissociates in the sense of it loses free protons. But it doesn't break down in the sense of decomposition, where these phosphodiester bonds just break apart in the solvent. And what I find really weird about this is that no matter how many people have, just let me get this point, no matter how many people have told you that that dissolve doesn't mean break down, you keep using those two words interchangeably. You just don't seem to accept that so many people have said that's not what dissolve means. When you say, well, my hopes have dissolved, that's what it means. But in chemistry, that's not what dissolve means. It literally means enter into solution. And you keep saying that. And then you just referred to, you said, I just showed you a video, the one that Daryl Sauer, I hope he sends me a message to tell me how to pronounce his name properly, had found, and that Fiona had reshared. You showed that video where you said, this guy's talking about it breaking down. No, the only breaking that's going on in that video is that you have these, he said sugar, but glycoaldehyde molecules one after another, and then they come apart. The molecules separate from other molecules. The molecules themselves don't break down. That to me is the really critical difference. Is the glycoaldehyde or the table sugar, the sucrose example, the molecules are bonded by intermolecular bonds. And in solution, the intermolecular bonds break apart and the molecules break apart from each other. But the molecules themselves don't break down. And the same for DNA. It goes into solution. And but the DNA molecule doesn't break down in any sense beyond the ejection of a
Well, here's the point. This is what Fiona agreed on. I'm going to screen share one more time. Fiona agreed that DNA dissolves, and the only thing that she would say was that it would enter into solution. The problem would be is that when something's entering into a solution, can you see what I'm screen sharing?
Not yet. You're still on your icon there. I've got you presented, but can
you see what I'm screen sharing now?
Your screen share hasn't kicked on. I wonder if is it the bandwidth setting or you screen share it fine before. It worked good before.
Okay, can you see what I'm screen sharing now?
Oh, there we are. You're on now. Yeah.
What me and Fiona agreed on was that DNA dissolves. That's what we agreed on. That DNA dissolves. I think the only thing that she said was that it breaks down in solution, and she broke down what happens basically when you're getting the pellets, and you know how it happens when something precipitates inside of your solution. That's what she was basically breaking down. And when we were speaking, she basically repeated that over and over again. All she would say was that it enters into solution, and I asked her if we agree that DNA is soluble, and she agrees to that. So where we agree is that DNA is soluble of a substance able to be dissolved, especially in water. The last video that we show, what does it have to do with? Let me see if I can find this. And I'm not even going to share it. I'm not even going to, because we all seen it already. The video that we just shown had to do with dissolving, how different covalence bonds dissolve. And if you listen to what he's explaining and what he's talking about, it is breaking down. This is the description that he's using for it to break down, and he explains how they're breaking down. So the definition of dissolve, the description of using dissolve as breaking down is specifically online with what happens when it dissolves. That is the main core issue right here at hand, is that if it dissolves, and if we're going to go by it breaking down, for example, the sugar that they were using, breaking down into different forms, well, what do you think is going to happen with DNA when if you apply that to the same level? It would be breaking down. So I want to share one other thing as well. This is what Fiona was using as an alternative method for DNA extraction. And she didn't read this part, but I'm going to read it for you guys so that you guys can check it out. It says the elution efficiency is dependent on the pH. The maximum elution efficiency is achieved between pH 7.0 and 8.5. When using water for elution, make sure the pH value is within the range. Store DNA at negative 20 degrees Celsius. When eluted with water, key word right there, store DNA at 20 degrees Celsius when eluted with water, since DNA may degrade in the absence of a buffering agent. Let me check out what degrade means right here.
Well, I think
so it's
whatever it means on the internet.
Well,
yeah.
I'm just saying to break down.
I don't care
to break down or to deteriorate chemically. So all of this is really coming down to the terminology that I'm using, and because that's really the only criticism that I'm hearing so far. I mean, even with you, there's really not too much for us to get into right here, except for that key word breaking down. Does DNA break down? Well, if it's soluble and it dissolves, well, then yes, it would be breaking down. And it seems like that's like the only thing going down here. So I mean,
well, no, that I can't let you try that. You said that to me in a comment earlier too about the sort of picking on the semantics of it. I mean, semantics come into an issue because if we can't understand each other, if we're not using words the same way, then if we don't ask each other, what do you mean by this word, or this is what I mean by that word, it's really hard to communicate. So we necessarily get snarled up in these semantic discussions, and nobody likes it. But it's helpful to do so. But let me be clear about this. It's not a semantic issue. Like I say, I'm willing to let somebody else use a word how they want to use the word. The issue is, as a matter of fact, do the phosphodiester bonds between nucleotides break down in water? Do they actually break the bonds and separate those things? And that's not a semantic issue. You can say you can use whatever word you want to use for it. I'm telling you, I don't think it's helping you to communicate or us to understand what you're trying to say when you use the word dissolve to mean break down, especially when you're talking about covalent bonds. Notice in both of those videos, there's only two types of bonds that he showed breaking. On the sodium chloride side, he showed ionic bonds separating and these things wandering around. On the other side, where it was all a covalent organic molecule, not an acid, he showed the intermolecular bonds, the very weak intermolecular bonds breaking down and these things sort of wandering off. He didn't show any example of covalent bonds breaking down by putting something into water. So what you're doing is you're giving us all these examples of various bonds that break down, ionic bonds in this molecule, in this compound, and intermolecular bonds in this other organic compound, not an organic acid. And you're saying, well, since this guy on YouTube says that things break down, that the bonds will break in the presence of water, well, then obviously the phosphodiester bonds are going to break. And for me, what it comes down to is
well, that's I don't think that's a fair analysis. I mean, I'm explaining in detail why DNA breaks down in water. We understand it's water soluble, but what is making DNA break down in water? And I brought in, for example, the what did I bring in? I brought in the polyanion in DNA and the cation in sodium. That's what's basically protecting it. So it's that on the sugar phosphate backbone. If you're going to screw with that, then it's going to render it unstable. So that's basically what I was getting at. It's not like just vaguely saying anything. It's specifically there's a part in the DNA molecule that if screwed with is going to mess up the strand.
I don't think there's really much.
I mean, even if you're gonna say, like I brought up hydrofluoric acid with a hydrogen ion, you could remove one of the ions when it disassociates, but you can then make it back into hydrofluoric acid. But removing one of the fluoride ions is still, it's not going to be a hydrofluoric acid again. if you get what I'm saying. You can do the same thing with, same thing happens actually with a water molecule when it becomes an OH when you're introducing NH3 or ammonia. So you can't just say, well, just because you're introducing a certain chemical or different chemicals react differently, that therefore, well, DNA is going to be fine. DNA is a delicate thing. It's very fragile, especially if we're going to talking about DNA, RNA, which is more fragile if we're going to be speaking in the context of abiogenesis, because some people believe that RNA was a precursor to DNA. RNA is even more fragile than DNA is. So the point being is that needing DNA and specific sequences, or needing RNA, even that is really important here. And you can't just say, well, it can be altered this way or the other, or you can, it'll be fine. It doesn't work that way.
I'm glad you said that, actually, because I think you're rescuing us from this problem now. If we're just saying the same thing over and over again. So because I do think that the DNA the strand itself doesn't break down in water. Those components don't, the nucleotides don't just pop apart because you put it in water. And I mean, to me, on that issue, the proof of the pudding's in the tasting. We just have to see, do we know anybody who's ever put DNA in water and seen if you could still sequence it? And we do, and we know several people who've done so, and there's lots of literature on it. And it's just, to me, the proof of the pudding's in the tasting. I don't even know enough about that chemistry to make sort of an argument predicting. Well, no, I could, because I'd say those covalent bonds wouldn't break down.
Well, I'd say this. We also got to remember that DNA is a weak acid too. So I wouldn't dispute as to whether or not they're using water in different processes. But like we just read with Fiona's little article that she showed, you got to keep it a certain way, and it's got to be used a certain way. And on top of that, if it's left too long, it might dissolve. It might take time for it to dissolve as well, if you get what I'm trying to say. Like I brought up different salts and different acids, they dissolve at a different rate than others. So that's something as well. I wouldn't dispute that water could be used, but what is the process and how it's being used? Was there elements introduced first, and did that protect it beforehand? And what happened afterwards? Is it like they're keeping it in a solution of water for like days and days and days at a time without any protection on it at all?
I believe so. I mean, the thing is that the thing you just showed about the way to store it as part of that one particular process, I'm sort of on the back foot there, because I don't know what that process is. I didn't see any of that stuff that Fiona had posted. Because to be honest with you, I didn't really have time, but I'm not really that interested in what are the specific steps in a laboratory procedure that gets you to a certain point with DNA extraction and then get it ready for sequencing and stuff. I mean, there are people who are utterly fascinated with that. Evidently, Fiona's invested hours and hours and days of her life actually doing that. And I just can't really muster a bunch of enthusiasm.
On a chemical, I think that the difference would be I would agree that Fiona was doing that on a regular basis, but I think that the disagreement is her understanding the process versus that of what a chemist would look at on a chemical level. So I mean, Fiona's a smart woman; she knows exactly how the process is done about. But I have to disagree, because even the sources that she's giving me, they seem to confirm what I'm saying. So I don't want to bring myself into a position to where I'm just taking her word for it. Being that, me and Fiona do have a history. If she were to show me where I'm wrong in anything that I'm saying, yeah, I'd put up a video saying, you know what, you're correct. But it seems like even her sources are saying the same thing, that DNA will degrade in water if it's kept it along. Or if it's kept too long in water. So my problem, I mean, this is I think a minor issue that I kind of feel like a lot of people are being stubborn with. Whether it's not the case fully that DNA degrades in water, I think the evidence pretty much shows that it pretty obviously is going to degrade in water if it's left to water in water without something to intervene and to protect the DNA strand. But even if this wasn't the case, I mean, there are many more reasons why abiogenesis is not valid. This is just a side issue or a minor issue.
Yeah, please do rescue us from the because again, I just don't think the covalent bonds break down in water, and I just think the proof of the pudding's in the tasting, right? I mean, have people done it? Why don't we let that go aside then and say, answer that question. Is so many of us have watched this and just went, what does it matter? Because the other thing I find weird about it is that I don't know that anyone is arguing that DNA floated around randomly in an ocean somewhere. My understanding is that by the time DNA comes on the scene, there's already been like a membrane, right? Some sort of phospholipid, so polar head, non-polar tail, some protective membrane, and there may be some collection of salts inside these vesicles or inside the membrane itself or whatever else that would stabilize DNA by the time DNA comes on the scene, right? I mean, my understanding of that was that by the time it went to the double helix structure and the deoxyribonucleic acid as opposed to ribonucleic acid, the sort of
Like
proto cell thing had already existed, was my understanding. So,
well, I'd say that just getting that to a position to where it would be protected, like you have in the cytosol inside of the cell, that is a big step in just utilizing DNA. I mean, even because some people like to try to say, well, viruses were the precursors, or you know things like that. But the problem is, some people try to say things like that, or maybe it was a virus stuck in some sort of a lipid vacuole or something like that. But the problem is that, okay, well, what about viruses? I mean, viruses, they need host cells. They're dependent on host cells to be able to reproduce and survive. So I mean, there's just a big problem. And if you're going to try to make it to an established system of life, the cell with the cytosol, the proteins, these different things, the salts are inside the cytosol as well that help to protect DNA as well. That's a huge step.
Yeah. Well, I think there are a couple of things about this whole discussion about abiogenesis and about criticisms of it that are sort of big mistakes in sort of how we start to talk about it. One of them is to look at a modern cell and say, look, for the interior of the cell, the cytosol, the cytoplasm, all this stuff to function in a way so that the cell isn't just poisoning itself. It's not sufficient to have a membrane, right? I mean, think on that. I mean, the membrane is a really helpful thing. The phospholipid bilayer. It's not even a phospholipid layer. It's a phospholipid bilayer with the non-polar tails oriented inward to each other, and then the polar heads oriented both outward and inward. I mean, it's a fascinating system, but it's not even enough. That wouldn't even be enough to keep a cell alive. What you also need to have is some sort of regulatory mechanism for getting stuff in and out, and you need gates that penetrate through the membrane. So there's actually membrane-bound, machinery and gates and things like that to do things like to pump sodium in or pump sodium out or whatever you need to keep the cell in the state that it needs to be so that all the internal workings go on. You actually need doors and windows in your phospholipid bilayer. The cell membrane has to have doors and windows in it. Well, what are you going to make those doors and windows out of? My cells have membrane-bound proteins. So amino acids ordered together into a chain and then put into a tertiary structure and embedded in the wall of when I say the wall of the cell, I don't mean the plant cell wall. I mean the membrane. They're membrane bound in there. So it's you look at a modern cell and you say, well, how could those conditions have been created in these earlier proto cells? Because proteins might not have been on the scene yet. Certainly not complex DNA encoded proteins like we say today. I just find it very difficult to talk about what we see in modern systems and say, well, then how did that work in RNA world or in these proto systems? Because obviously they didn't exist then. That may be your point. I think intelligent design says, how did these systems come to be if they weren't there? But I'll tell you the second thing that I think is a real false start in this conversation is when you hear people on the ID side say things like, and I have heard you say this once, when they give you a probability for something, when they talk about, well, look, what's the probability of a DNA molecule assembling itself? If we just took a 100 nucleotide sequence, that means the first, and it has to be a particular sequence. That means the first one's got to be this. That's a 1 in 4 chance, and a 1 in 4 chance, and a 1 in 4 chance. That means that you take 4 to the 100th power, 4 multiplied by itself 100 times over and over again, and the odds are 1 in that number. And of course, it's incredibly huge. Well, that's fascinating. Except the thing is, that's the calculation you would make if you had exactly 100 nucleotides. I may have said amino acids again before, I screwed it up twice. If you had exactly 100 nucleotides that needed to be put in that order, sitting in a container, and they spontaneously hooked onto each other one after another, right? That's the calculation you would make if you already started with exactly 1,000, is that what I said, of those things. Maybe I said 100, whatever it was. It had 100 of those nucleotides, and they hooked themselves together to form precisely one molecule. And they'll give you, well, this number is 1 in a bazillion or whatever. Well, first off, nobody thinks that nucleotides, right, that deoxyribose form, got together as a group of 1,000 and then ordered themselves together into exactly one molecule. There's like 7 different things wrong with that description. I just think so. Let me wrap up on this. I just think so many of these discussions about how well abiogenesis doesn't work is based on this idea that we look at how things work in these modern cells, and then we do these crazy probability calculations that nobody's proposing that's how it was done. And it just sort of leaves me wondering, okay, well, I guess you've defeated abiogenesis now. I'm going to apologize, Ronnie. That was awfully rambling. Why don't you use your judgment to extract something out of what I just said to make a point, or try.
Okay. So what it sounds like you're saying is that because we don't know specifically how it happened, we can't really draw any sort of criticism to begin with.
So listening, go ahead.
So yeah, I'm just basically asking, is that what your criticism is? It sounds like that's what you were trying to say at the end, is that because we don't know specifically how abiogenesis happened, it's unfair for us to draw any criticism that way, like a self-replicating whatever.
Yeah, no, that's not what I'm saying. But because I see what you're doing, it's 100% my fault. Because what I did was you had said something, and then I said, well, here's 2 things I think that's wrong with the way that we discuss abiogenesis. And then I went on these things. I don't think I was even responding to what you were saying. I apologize for that. I don't think I was actually giving you a rebuttal or a criticism of what you were saying. I just sort of had launched off on this other thing about the generic nature of how we discuss abiogenesis, and how I think that it's sometimes not really helpful, because those criticisms, like when people say, well, look, the DNA couldn't just swim around on its own, or when they say the DNA couldn't just assemble, the nucleotides couldn't just assemble themselves into a perfectly working strand of DNA. I think those are examples of a straw man criticism of abiogenesis, because they don't really reflect the thinking of how these systems developed in early proto-life. So I apologize, Ronnie, because I think I said it as if I was responding to what you were saying, but I was actually making a completely different point, and I kind of left you feeling like, how does that address what I'm saying? So no, but just to clarify, just to answer your question, no, I'm not saying that, well, because we don't know what the abiogenesis events were, then we shouldn't criticize any such theory. Obviously, that's great grounds right there to criticize it.
Well, I would just say that, all right, let's word it like this. Richard Dawkins has said that the more complex a system is, the more improbable that it is. So would you agree with his terminology on that the more complex a system is, the more improbable a situation is? And in the context of what he was saying, just in case anybody was asking.
What to ask you?
Yeah, he was saying it because of, basically God not existing, because God would have to be more complex than anything in nature. If he designed these things, he would be more improbable than where did God come from type of thing. He's more than likely not the result of what's happening.
I struggle with that idea that somehow God is complex, in the same way that I'm using a laptop here, and if I pull this cover off, it's complex. There's a lot of complicated stuff in there. When we talk about the complexity of an object in our universe of discourse, we're usually talking about the complexity of a physical object, right? And that's the organization of the matter that make up that object. And that's why I've never understood this issue. Like, what does it mean to say that God is complex? Because God isn't in any sense an organization of matter. So I don't really know how to talk about about a God's complexity. So I don't know that I really buy that point from Dawkins that God would be improbable for being too complex, because the complex arrangement of my notebook computer or the complex arrangement of my car, or the complex arrangement of my own body. Part of the evidence, these things are really complex, so they're improbable. These things, you know, what's the tornado in a junkyard turning into a 747, that sort of thing. Those things don't happen by accident. You don't get a tornado that assembles a 747. And when we talk about those examples, we're talking about the complexity of the physical arrangement of a bunch of physical things. I just don't see how that sort of an argument applies to God, because how do we say that God is complex or not?
So even just absent of God, would you say, like, the cell, a system of life, the cell, would you say that that would be complex? Do you think that it would be that would be improbable because of how complex that is? So that would fall into, you know, what we're saying here, improbability. Yeah.
There have to be some sort of process, and that is, you couldn't just take these molecules and put them together. I mean, I shouldn't even say the molecules, because how do you even get the molecules would include the biopolymers. You couldn't just take even the components of those biopolymers. So you had a bunch of amino acids, a bunch of nucleotides, a bunch of nucleosides, a bunch of phospholipids. Their ability to organize into a cell, to me, is exceedingly ridiculous. It just could not, it just wouldn't happen. So the only logical conclusion is that there is some process that put those things together, right?
Yeah, well, there's got to be some explanation for there to how it happened. And what I always ask is, what is the best explanation? What makes more sense based on what we see? So, I mean, if you have something as complex as a system that is the cell, and if we find systems in there that are congruent with what we observe coming from intelligence, then why is it that we do not come to the conclusion that intelligence is a better explanation than abiogenesis?
Yeah, so I mean, we're agreed that there's obviously something that led to it. I think that's a helpful point of agreement. But then you say intelligence. Now, I had a chance to listen to your discussion with Dave S. about this. I think that was a really helpful discussion. I think, you know, for a while I've been saying, you know, Ronnie, I'm sort of wondering, like, what is your point? Where does your argument go? And I think, and I've posted this effect on Google+, I think that in the last couple of months you've actually been able to flesh an argument out for us so that we can know what we're talking about. So if I understand you correctly, you're saying we see things in the cell, in so many things in biochemistry, in biology, that are like just impossibly unlikely to have assembled themselves. So, and we concede, as I certainly do, there has to be something, a process, some sort of rules that take place, some sort of guiding principles that make it so that these things work out. I would say that it's the laws of physics. It's just the laws of how the universe works. You're saying, well, no, we got to put in intelligence, and I think that's where most of us put on the brakes and say, and then now you're asking me, well, then why not intelligence? Why would you not include that intelligence is necessary? And the reason is, as I understand your argument, you're saying we see all these neat things in the world. You know, here's a smartphone battery, here's a USB key. There's all these wonderful things in our world that are clearly products of intelligence. Therefore, these complex things. You can see that it's an inferential argument, right? That everything we see that is complex physical arrangement of matter, is a product of intelligence, and we are complex physical arrangements of matter. Therefore, by
just to clarify briefly before you finish your point, is that I wouldn't say that everything that is complex is therefore design. I would say that if we're going to be honest about it, there are only specific things that we can say that are complex that are more than likely design.
Oh, can you think of something that's complex that isn't a product of intelligence or design?
Well, as a Christian, I would believe that, you know, everything came from God. I would say that, but
that's fair.
If we're going to try to infer honestly in an objective way, that I can't say that. For example, a snowflake is formed under a fairly simple process. We understand that. A lot of atheists like to look at that as if that's complex, but like you've heard me bring up before, motors and turbines, those specific type of operations and functions, that type of complexity, as far as we know, has only come from creative intelligence.
Right. And the thing is, though, everything that we've seen, all those examples, like the motors. By the way, let me say this first too. I heard somebody tell you in a Hangout, well, that motor, like the flagellum, all these things, that's not really a motor. And I don't take that stance. I think that's a mistake. I think if the word motor or the word machine is going to mean anything, you have to define it based on the properties of what a motor is or what a machine is, and you don't selectively apply it to things that are manufactured, right? So a person, you can look at the motor that's in my car, and you can say, well, that's a manufactured motor. But just because something isn't manufactured and you wouldn't call it, like a Ford Motor Company motor, that doesn't mean you can now say it's not a motor. The word machine in physics has a particular meaning. The word motor has a particular meaning, and I would concede that these structures you're talking about in cells are machinery, and the specific one you used is an example of a motor. But here's the thing: every machine, every motor, every device, every appliance, all these things that we see in our world that are complex and clearly products of design are things that, what's the backstory behind those things? Those are things that are created by specifically humans with hands and fingers and eyes and communication and ideas being handed down generation after generation. Plus, these are things that are big, right? So they're macroscopic things, right? That we take by taking materials and assembling of smelting and refining and doing these things in the world around us. So when you point to the bacterial flagellum, any sort of a motor or turbine or anything like that, and you say, well, gee, this is an awful like this motor that you see in your car. I say, well, then, okay, give me an example of give me one example of a microscopic motor device or something like that. I'm sort of losing my thought here.
So you're basically saying that because it's smaller, therefore we can't say that it's design?
No, I don't think that would exclude the possibility that it's design. I'm saying that it's a monkey wrench in the argument that you can look around the world and you see all these things that are amazing, obvious products of design, and they're all
well,
they
let's
all
look
have.
at it. Let's look at it like
there are several things that are in common amongst all the things that are designed. Number one, they're big. They're things that we build with our fingers and our hands and our eyes and our brains, and our ability to communicate with other people. I mean, do you think that this USB key would make any sense for somebody to sit down in a shop and to put this thing together? No. The reason that this thing makes sense is because of generation after generation after generation communicating ideas. All of these devices that you're talking about are the fruits of many, many, many features, including communication, the hand-me-down of technology from one generation to another.
Wouldn't you agree that the more advanced we're becoming, the smaller our technology tends to become? So the more advanced a civilization or intelligence, the better their capabilities are of doing things like, for example, computer chips or in computers. Where our technology is advancing and advancing and advancing, and the technology is becoming smaller. You can fit what used to be refrigerators full of, a warehouse full of computers, or the size of refrigerators, into the palm of your hands now.
Yeah.
So I mean, I think that most people understand that the smaller you make something, the more difficult it's going to try to be anyways. So if you have a motor or a turbine that's small the way that it is, it doesn't negate the fact at all that intelligence wasn't behind it. I'd say that it's actually the reverse of that. I'd say that it demonstrates that whoever this intelligent person was extremely intelligent.
Yeah, well, there's one point that I just cannot argue with, because how would you defeat this? But the idea that if there were a being of sufficient intelligence, like if there was a creator God that sat down and said, or sat down, whatever that means for a God, and wanted things to turn out the way they have, then this is what would have happened. This God would have made things the way they are. If there was a God like when you describe, or you and many other people describe an ultra-powerful God, that God would be able to create a universe, create time, space, energy, matter, and create the physical rules under which these things would interact, so that we would see what we've seen. We would see an expanding universe. We would see accretion disks and cooling into blobs, and then mountains and waters and streams forming, and we would see abiogenesis, and we would see evolution, and we would see all these things that the evangelicals object to, by the way, right? That they say that these things couldn't happen. Once you start talking about these molecular machines, like on the these nanoscale machinery that quite obviously evolved in biological systems, to say that somebody could have designed that. Okay, well, sure, somebody could have designed that.
But see, how do you say that though? I mean, like in the middle of when you were talking, you said that it quite obviously evolved into systems. But the idea is, for example, homologous proteins with the bacterium flagellum, that the type 3 secretory system that slowly led up to the complexity of the bacterium flagellum, the type 3 secretory system. The problem is that doesn't therefore indicate that it can happen. So what would be the evidence of anatomical features or functions like the bacterium flagellum actually being produced in a way to where we can actually see that the cause, or the speculation of the cause, which was natural selection and mutation, is adequate enough to justify and prove the effect, which is these anatomical features and functions?
I think you got the right read on it. That it's the similarities, right? It's the patterns of similarities and differences that suggest a nested hierarchy that leads someone to believe that these are molecules, or protein molecules, that these systems have evolved, because you see sort of these cousin systems. Now, I'm going to grant that that's unsatisfying. I would agree with you if you say, well, that doesn't prove, just because you see the similarities, these patterns of similarities and differences. Here you've got some bacteria which are really, really a lot like each other. And they're also kind of like these other bacteria over here, which are a lot like each other, but they're not quite as much alike each other, between groups.
Well, of course. Because don't you think about it, like if you have 98% of all the species extinct, and we have a very large variety in our time frame that we're in now of lions and tigers and gators and all sorts of different species and pathogens and all sorts of different organisms on this planet just today, it wouldn't be surprising that you'd be able to find through the expanse of time, with all of these species, to where you would be able to look at things and see patterns. But looking patterns, and even if you're seeing a gradual step-by-step process, doesn't mean that therefore they evolved. I could sit over here and say that some creator that came in may have produced mass extinctions and decided to make a different variety of life. It would be basically on the same level. What divides that and what makes whatever explanation better would be as to whether or not we can prove a cause and effect that can justify this case that we're trying to make.
Yeah, well, I agree. This is one other thing that happens in the conversation. Not that you're doing it, but this is something that happens in the conversation a lot. Is that someone will, like a creationist, Kent Hovind does this a lot, where he'll ask a question. Actually, Ray Comfort's bad for it too. He'll ask a question, give me an example of information being added to the genome. So then the person will say, oh, well, here's an example, myelinase or whatever. And then the creationist will say, well, that doesn't prove that man came from monkeys. That doesn't prove evolution is true. That doesn't prove common ancestry. Well, that's not what you were asked, right? But anyway, there's a reason why I mention this, and that's because I agree with you, and it might surprise you that I would readily concede that we can look at these patterns of similarities and differences amongst bacteria, or amongst mammals, or amongst all vertebrates. And that doesn't prove common ancestry, right? It makes sense that a creator, if there was separate and special creation, reused some of these ideas and created these interconnections. Isn't it great that these other animals we live on the planet are made out of meat? Because we need that to survive. They're made out of proteins. We need those amino acids. Isn't it great that the plants that we share the planet with have all of these nutrients that we need in our bodies? It wouldn't make much sense if we were the only life on the planet that was carbon-based and everything else was silicon-based, and eating it wouldn't nurture us. So it makes sense to me that yes, we would see these similarities, even if a creator God created us separately and specially. It would also make sense to me that we see this pattern of similarities and difference if we're all related. So I don't think that the patterns of similarities and differences prove it. It's got to be taken in the context of this other evidence. So for example, you got G-Man repeatedly asking the same dumbass question. It doesn't matter how many times people tell him, show me proof that a dog can turn into a non-dog. He doesn't mean have puppies that are not puppies. He means over time, after many generations, these are dogs, breed, now they're not dogs anymore. Everybody tells them that's stupid, that's not what evolution is. Okay, whatever, he's not going to change.
But isn't that what evolution is, though, when you think about it? Change over time, species and become distinct from species B. So I think because I think that is what he's trying to say. He's trying to say that when a dog gives birth to a non-dog, that its offspring eventually through time is going to become something that is distinct from the dog that it is now. He's just not elaborating.
Not distinct, more specialized. This is the thing, again, so you can look at the patterns of similarities and differences and do all the genetic hierarchy mapping that you want to do. And that's all very informative and fascinating. But it's also taken into context with these other observations of what we've known, what we've seen in the physical world. And that is, let's take a look at the history of dogs. Dogs don't turn into non-dogs. In fact, all dogs are wolves. Wolves didn't even turn into non-dogs. Wolves, some of the wolves.
Yeah, I know. I get what you're saying. I get what you're saying.
Okay.
The dogs. So
let's back up from the wolves.
The wolves, their predecessors, they were still whatever they were. And I've heard that before, but I think that the distinction here is that you can't really speak from an objective standpoint from what you already agreed to. Like this is like
giving you different evidence. I'm giving you a different line of evidence. Okay, so you've heard the thing about the dogs, right? That all dogs are still wolves, right?
Yeah.
And all those wolves are from this ancient bear dog looking thing, right? and they're all still myocytes, right? So this myocyte is this weird sort of like generic kind of dog looking animal with the teeth and the four legs and the claws and a tail. But to look at it, you wouldn't recognize as a dog. It's definitely sort of dog-like. Okay, so you've heard that before, right? That you're fine with that. What do we do? And by the way, you can also trace this geographically, right? When you dig down through the layers, you find that here's a geographical region where we find these type of wolves, and then as you dig down, you'll find that they had a different dispersion. They used to be over here a little bit, and before that they had a little bit of a bigger area. Right, but then during this era, I'm trying to do this with my hands, is that as you go down through the depths, you don't just go down like this. You find those dog fossils here, and then in a lower layer you find them a little bit over here. In a lower layer you find them in a bigger area, and in a lower layer you might find them in a slightly smaller area. And you can track the migration pattern of the ancestors of wolves as they spread out and lost area over many, many generations on their path from being an ancient myocyte to being modern dogs. So if you now ask me, well, where do these dogs come from? I say, well, look, we can look at the geographical distribution. They used to live here, they used to live there, they used to live there, they used to have eyes like this and teeth like that and tails like that, because we have all the fossil evidence on this long history for the dogs. Okay.
Well, see, the problem is that the fossil evidence, this is why I don't really like to get into evolution, because the fossil evidence, it doesn't really prove anything. The fossil evidence, even if they're dispersed throughout the geological timescale, you have to have evidence for the changes in anatomical features and functions. You have to have something to prove that could actually happen. You can't just say, well, look, we see fossils all the way throughout the geological timescale, because what that does is that brings us into things from a creationist standpoint of, well, does the Great Flood explain the disposition or the differences in the fossil record to where everything is dispersed in different directions? Why is it that we have the Precambrian era then, with the 540 or 50 million years of the Precambrian era, that's 88% of the geological timescale, and you see a lot of the phyla there at the beginning of the Cambrian era, we only know 12% of it. So what happens when you get into the fossil record, when you get into fossils, you're just basically tracing things back down to your interpretation of the fossil record. I think that instead what's really, really important is seeing, okay, what can we do with the evidence now, with the experiments now, or what we observe now that can demonstrate a cause leading to this effect, where we can see that this species, it is justified to say that this species over time can evolve to this complexity that we're seeing later on down the line in the fossil record.
Well, okay, you kind of perhaps by accident kind of derailed my point there about the fossils, and you started talking about we need evidence that things can change. I think that when you look through the fossil record, you do see generation after generation of morphological changes, unless you believe that at this particular layer, when we're talking about the dogs, for example, that like here are these things that don't quite look like dogs yet, but they look more like dogs than the things in the layer below, and then suddenly they all went extinct. But the very next year, God specially created something that looked slightly more like a dog than the things that just went extinct. Like, I mean, to me, that's crazy. But let me make my point about when you say, like, quite often creationists use the term, well, that single observation doesn't prove evolution. And I would always agree with that. Anytime I give some evidence for evolution, if a creation ever says to me, well, that single thing you're telling me doesn't prove evolution, I'll say, yeah, of course it doesn't. What it is, it's coupled with.
Well, here's the problem. Here's the problem.
No. You walked off of this other point about the thing of Precambrian and stuff when I didn't get to make my point about the fossils. Okay, this is the thing that's very compelling to me. So I want to share this with you. Let's say, okay, set aside the dog thing. You say you've heard that before. Let's talk about the cats. Do the same thing with cats, and we go back and we look and we see here's a geographical distribution of the wild cat, the predecessors to our modern tame cats, and we see what their geographical distribution was. And you go back and you go back and you say, well, they were here, they were here, they were here, and we go back and we find, well, they actually used to be much bigger, right? And they used to have broader bodies, right, and longer teeth, right? And you can go back and see these morphological changes in the history. Neff would not call them morphological changes. Let's call them morphological adjustments to make Nephilim Free happy. As you go back through the geographical, like down, follow their geographical pattern throughout history, you can see what these things used to look like, what the ancestors of modern cats used to look like as you trace back their routes. Here's the wacky thing. Do you know where you get to? The Miacids, the same place that you got to in tracing back dog history. So you got your dogs and you got your cats, and you can do this with just about any pair of species, is you can trace those that would leave fossils, of course, is that you can say, well, here are these animals and here are these animals, and you trace them back, their geographical, and you map their morphological changes that happen as you go back in time, and you end up, boom, at the same creature. There's a straight line between ancient Miacids going to a weird bear dog looking thing to bears and to dog looking things, wolves and coyotes and foxes and things like that, and a straight line from that same starting point through to all the various feliform creatures along the way, including your hyenas and including your panthera, and all the way on across and down to modern cats.
Okay,
that to me is very compelling.
Well, it's compelling to you because you're looking at the interpretation of events that made these things happen in a certain way to where you think that happened. But the point would be is that even still, the fossil record does not and cannot prove anything until you have some sort of proven causal demonstration that can demonstrate that the type of anatomical features that are being called into question across the board can actually happen. So, I mean, like, for example, I brought this up before, the differences in between how birds breathe and reptiles breathe, or the differences between mammals breathe and reptiles breathe. We breathe in up and down through our diaphragm. The birds, they breathe in through different chambers. They breathe in through different chambers, and they go in and circulate, so they grab a hold of oxygen better. They can breathe better. That helps them when they're actually in flight as well. So the point is that those anatomical features and functions changing, you can sit over here and line up cars and skateboards and bicycles and look at different patterns in them, but that doesn't prove anything. The same way that you can look in the clouds and see certain shapes and patterns that look like objects that you know of, but that doesn't prove anything. That's. Well,
I got to stop you there, and I apologize.
Well, it's basically pattern seeking. So I think like the main points, what we were talking about a while ago, which led us to here, is like the motor. Like, is there any sort of demonstration that can lead up to that complexity, rather than just saying, well, okay, we have the type 3 secretory system, and it shares homologous genes, or it's homologous proteins. Homologous proteins with the bacterium flagellum, so therefore it came from each other. There's a big gap there of explanations.
That's right.
To get across.
and we should probably let's do you want to do 10 more minutes or 15 or something? We did commit to each other. We were going to sort of keep it relatively short, but I'm glad we got to this topic, and I suggest that we just got to do another hangout because this is fun. I do want to say that you did just do the thing that I was complaining about before of saying, well, that doesn't prove that. So for example, when I was laying out about the dog history, I made it very clear that what we're not doing. Do you know the famous spoon fork display? The creationists loved this one a few years ago. They got like a whole bunch of spoons and forks and a spork, and they put them in order, and of like sort of like, well, here's the spoon end, and this one looks a little more forky, and this one even more forky. We're at the spork now, and then we're definitely on more forky than spoony. And they put them out there and they said, aha, look what I did. I put these things in order from this one being more, and there's gradual change to the other one. Therefore, the fork evolved from the spoon. Ha, ha, ha. Aren't evolutionists stupid because you can do this with anything? You just suggested that that's what they do. You said, well, the reason that I accept this interpretation of the ancient mice, is it mice or mycoid? Which one did I say? Is going to the cats and separately going to the dogs. You said, well, that's because it feeds into your already existing interpretation. And you said just because they happen to look alike, but that's not what I said. I said you can trace these things geographically as you go down through the column. So what you're doing is you're mapping out the morphological features, the geographical extents, and as you go down through the geological column.
Well, see, what you're doing here, though, is that you're mentioning a very broad, a broad description of different creatures down a line. Now, we can look at those things and we can see, okay, is this actually true? Is that actually the case that you're seeing that type of order that you're looking at? But let's just go back down to the Precambrian era. The Precambrian era right there, most of the phyla are already there at the Cambrian. So if 88% of the geological timescale, which had different effects as well, it wasn't just about life to non-life and so forth. If we don't know much about that, then where is the evidence to where that change can actually happen to these different phyla coming into existence? You can't just sit over here and say that, well, we have a line that we're looking down all the way down to an extent hundreds of thousands of years ago, so you can see a complexity changing. Because I would be more than willing to bet this list that we're talking about right here, we can find certain species that are found thousands of years ago that would be disputed as to whether or not they would be living fossils or something. So I would disagree that the line that you're speaking about is as direct as you're making it sound. Like you're seeing the complexity leading up to diversion to the dogs and the cats and so forth. So instead of getting into such a broad topic as the expansion of all the different diversity of life here on Earth, which we can't really verify and see if that's true anyways. What's more important is to see, is there something in our time now, something tangible that we can, this is one of the reasons why I don't like to get into that, because that is the most important fundamental question. Do we have a proven mechanism that can lead to that complexity? Yeah.
And that's an area that I kind of wish I knew a little bit more about, but I do have, because I want to address your point too about the you want to see evidence that these kind of changes can happen. I kind of have to concede, and this may only be my knowledge, right? There, maybe someone else would come in and say, oh no, HogTie didn't realize this. There's more to it than that. I don't know. But the reason I was using the example of the ancient carnivora and the feliform carnivora and the caniform carnivora and splitting off into very clearly bear dog line and cat line is because they're familiar animals, and there are arrays of these things available on the internet. So if you don't believe me that we have a chain of fossils that are mapped out in a geographical distribution that lead back to the same creatures with the same morphology and the same geographical thing. So it's very, very obvious that cats, dogs, bears, foxes, coyotes, hyenas all have the same common ancestor. This is something that's very easy for people to verify and to look at themselves and understand it. Where once you start talking about the bacterial flagellum and these motors and the subunits of proteins and stuff, it's a little bit harder for people to get, and as I say, sort of rubs against the boundaries of my interest. But you do make a good point when you say, well, what we need to see is a demonstration that these changes can happen nowadays, and I do think we have that, because like things like the bacterial flagellum and what these things are protein based, and we see new proteins appearing. The major criticism of of evolution, especially at the molecular level, is that information cannot be added to the genome, and it certainly can.
Well,
and we have examples of it.
Well,
and,
I got
and
like
not only we see examples, we see effective examples
well,
where the thing that's created is actually a new protein that never existed before.
I would disagree with to the extent of what you're saying right there. There's about like 6 or 7 directions that I can go with what you just said. But there's one thing, okay, that is a little bit more simple that we should dive into right here is, okay, let's say you were able to get the type of proteins that are needed for life. Let's just say that you were. Specifically, we're talking about the bacterium flagellum, right? The proteins. How is it that developing a brick is evidence that a house can be built? Or if I had a car being made, like I was able to produce
the evidence you asked for.
Well, let's like a car, the tire, the rubber in the tire. Let's just assume that you can get that formed, right? How would that prove that therefore can lead to the complexity of a car having a piece of material?
Of course not. Of course it doesn't. But that was my point earlier about you guys always ask for, well, give me an example of this. Give me evidence for that. And then upon having that presented, you say, yeah, but that doesn't prove the whole theory of evolution, right? Like, that's a constant rhythm of this conversation. And I wish more so-called evolutionists would pick up on that and point out to people that when you're asked, like what in that movie Ray Comfort had done, where he interviewed a very grumpy P.Z. Myers, when he asked him for an example of evolution, observed evolution in the modern era, P.Z. Myers gave him an example about either a bacterial change, a new protein, or I believe it was speciation. And he goes, yeah, but they're still bacteria. Yeah, well, you didn't ask for an example of a bacteria turning into something that wasn't bacteria.
Well, specifically what I asked for, I don't know what Ray Comfort was asking for, because I don't really follow Ray Comfort, but I'm asking specifically for new changes in anatomical features and functions. Specifically, I mentioned the bacterium flagellum. So what I'm specifically asking for is evidence that any experimental changes can demonstrate a cause that can lead to the effect of the bacterium flagellum, a new bodily structure or function like the bacterium flagellum. So I think that the problem isn't necessarily the question that I'm asking. I think it's more so how it's being answered, because you can't just
it's not the question or the answer. It's the reaction to the answer. It's when you ask for, and not you particularly, but just a generic stand-in creationist says, well, give me an example of this. And then when furnished with that example, you say, yeah, but that doesn't prove that the whole car came out. Your example about the tire in the car. So you'd ask for an example of, of a genetic change, right? Of a change. I take the position that new information can be added to the genome, and specifically effective information. That is, it carries the effect of actually creating new things, like a protein that didn't used to exist. And then you're saying, oh, well, even if you could create a tire, that doesn't mean that you could create a car, right? And that's not what you asked for. By the way, we should.
Well, I think what I asked. I was just going to say that specifically. I don't even think we really got into DNA at all, but specifically, I was on the motor, the bacterium flagellum. So I just think that. Don't you see a pattern? Let me just change the topic then, because I don't think we're going to go anywhere with that anyways, because the bacterium flagellum, the new bodily structure. Yeah, the new bodily structure, that's what I was trying to get at. But don't you see a pattern when you're looking at certain things? Like when we're talking about DNA, it's a computer code, it's information. That's what we'll say. It's got certain structure and operation that seems to mirror our development from intelligence. Intelligence produced computer codes. Not only that, a 3 out of 4 error correcting code, which it more indicates that it's was built by intelligence. Okay, the answer is, well, information theory or Shannon information. You can deal with the reduction of uncertainty with Shannon information, so that proves, or that's the type of information that it is. And there's like confusion there, and it moves on to different topics with information. Okay, so that's one thing right there. Then you move on to the ATP synthase, how these hydrogen ion gradients, they go in through the complex, they cause that C ring to spin and turn. It's a turbine. Oh well, it's nothing. It's just analogous to a turbine.
Oh, I agree.
So then you move on to something else, like the motor inside of the bacterium flagellum. It's got bushings and bearings and so forth. It operates and functions and operates like a motor. Oh, well, you know, it's type 3 secretory system. So it's like you see a pattern of things that we're finding, and the automatic inference is repeatedly like, okay, well, it comes from intelligence. But there's always like some sort of like, well, we speculate that it was something that led up to this, but there's never a cause or proof to show that there's an alternative that can make that happen. So it's like the answer is it looks like a duck, quacks like a duck, talks like a duck, but it's actually a cow.
Yeah,
I mean, that's what it comes off to people that are on the other side of it. It's like there's never really been anything, as far as I've heard, that's been like any sort of discrediting. It's like a way to sort of push it under the rug, as far as I've seen.
Yeah, you know, I'd say I did really want to kind of wrap up by 5:30 because I do have some other things to do this evening, and I like the energy. Like we just got to a point now where we know we have all these other issues to discuss. So I think we just got to put a pin in it and come back to it later. I absolutely do want you to go to your channel now and make a video that says when you raise that last point, HogTie ran away and closed the Hangout. Scared.
I'm not going to do it.
Yeah. Well, do we have? Is there any other point that we can sort of make in closing? I mean, I think we've got a to-do list of other things to talk about. I mean, I guess I want to say I've had some. For months now, I've had some concerns about the nature of the conversation, not just with you, but I see a lot of people. You know, I do think G-Man's kind of turned into a grumpy sandy vagina lately, and he's just sitting there arguing, complaining to people about, oh, you're scared and blah blah blah. And with let's not talk about him because he's not here to defend himself. But with you, it seems like we've really got into this discussion about, well, whether or not Ronnie knows something, or whether or not Ronnie's smart enough to understand what's being explained to him. And I don't even think it's amusing anymore. I mean, I think it's weird that that's gotten to be a topic. I don't know. I maybe I don't want to venture into that right now. You can say what you want to say. I want to give you a chance to sort of give us, without you and I arguing about it, just give us your side of, like, what do you think is going on? Why are we in this discussion about you saying that Sam knows something or Sam's got something wrong, and people saying that you know whatever? And I just want to give you a chance to sort of express your thoughts on that and not really argue about it, because it just, do you think it is good for the conversation to talk about those things, or bad for the conversation? What do you think?
Well, I think that talking about anybody and insulting them like that shows low character. And if I am somebody that shouldn't be taken seriously, then obviously, why am I taken seriously? I mean, it's not just it's not, you know, any random person, but you find somebody that gets something wrong, you know, you just ignore them. Why would you take them seriously? But when they're paying attention to me, I think it's obvious that they do take what I'm saying seriously. I mean, not one time have I ever said that I'm, you know, an expert in everything and that I know more than everybody else about every given topic. But I do say that if somebody's wrong, I'm going to stand my ground and agree with, talk about what I'm talking about. I mean, there doesn't seem to be a problem with, you know, like I'll watch some of JD Kane's hangouts or somebody else's hangouts, and there doesn't seem to be any problem with any other atheist talking boldly or confidently about the things in evolution and mentioning certain things. But as soon as I start talking about something, for some reason, the demand is, where are your credentials? We want to see where you've gone to school at. So there's this behavior there's a double standard very clearly, and it doesn't seem to be like, you know, where people are. It's like people are trying to like push me under the rug or discredit me a certain way so that they don't have to deal or listen to what I'm saying to them.
Yeah,
that's how it comes off.
I do think that I've kind of had enough of the discussion about where are Ronnie's credentials. I think that where that, I mean, the thing is that doesn't come out of the blue. I mean, there's a history leading up to that, including accusations from some of your brothers, perhaps from you briefly, though I think you dropped it, that Fiona's actually lying. Fiona faked having a PhD for whatever purpose. I don't know why somebody would do that. But I mean, there's these accusations that, well, this guy doesn't know this guy doesn't know that, you know, he can't really be a scientist. He can't really, you know, Fiona's faking this PhD and whatnot. I don't know of any occasion that you've come on and claimed that you had a degree in something. And in any case, I don't even like the discussion about who's got what credentials, because, you know, honestly, having a PhD doesn't mean you're an expert in the particular topic at hand. I mean, you're certainly got to be an expert in something to get a PhD, but you don't have to be an expert in the particular topic we're discussing. Can we not just focus on the information? But I do think that it's unfair to mischaracterize it as, well, the atheists are always picking on you for your credentials, because your side quite often raises that issue, and not raises it in asking for it, raise it in outright accusing other people of lying about their
well, it has to do with certain things that Fiona said. Like, I've said that I've questioned Fiona's credentials, but then when she showed me her credentials, I've realized, okay, well, she's obviously telling the truth about her credentials because of some of the things that she said to me. But there are other people, I'm not going to deny it, other people, they probably don't believe that she has the credentials, and I can't really do anything about what they're saying. I haven't actually dealt with
I think they're trolling.
Well, no, some of the people I don't really talk to anymore, not because, you know, I don't want to talk to them, it's just that I've lost contact with them because I've just been away from YouTube for a long time. I'm not as active as a lot of other people who are online, so I just lose touch with people from time to time.
I think a lot of those people do it to piss her off. I think a vice of Fiona's that I wonder if she would admit herself. I've not heard her admit this. I would encourage her to admit this. She tends to get rather easily offended, you know, and she, I don't know if she'll be happy I said that or not, but she's had, you know, I mean, people don't like being insulted and whatnot, but she doesn't play the victim card half as much as G-Man, who that guy has called 11 people a racist in the last 4 days. Like, he just, you know, he's a victim. It's persecution, blah, blah, blah. Fiona has just a touch of that, and doesn't compare to anyone else, but she does tend to say, you know, somebody says something to insult her.
Well, I think that G-Man called Fiona a racist because Fiona had.
Oh, he did?
I think he might. If that's what you're referring to, because of the picture that he had on her channel with the feather on my head. So that's probably what he was referring to.
No, I don't know that he'd ever said that about her. I wonder if we should screw it. I opened a can of worms on that anyway. Let's talk about the feather thing. I didn't know that was on there until about 2 or 3 weeks ago. You guys were in a Hangout, and you guys were incessantly complaining about Fiona. You guys, that particular Hangout was like wow, it was, she should have just called it the Fiona Show and let's complain about Fiona. And at one point somebody was screen sharing. It was you was screen sharing, I think. Was screen sharing Fiona's Google Plus page, and I think it was Beckel had said, "Hey, wait a second, put that up. Is that a feather?" And I was listening to the thing. I was in the kitchen doing something, and I heard you guys talking about it. They're a feather, and I came around to look, and I saw on the screen that it's like everybody has these distinctive features. I think it's hard to sort of make cartoons of people and sort of do these distinctive features. Like there's a HogTie character in the Sci-10 Atheist universe that I don't think is a very attractive fellow, and I think he's a bit of a jerk. Yeah. Like, you know, and okay, so how do we make a true empiricism character? What does Ronnie look like? And nobody's going to like how they look when they're characterized by a guy who makes videos that are intentionally insulting of people, right? Ozzy finds the Ozzy character funny. You know, he's this sort of hairy guy that wears a t-shirt and no pants ever. The Ozzy character in the Sci-10 universe doesn't ever wear pants. I've never. You know, it's sort of funny, but anyway, so the Ronnie character, how do we make him distinctive? Well, we're going to put a headband on and a feather. And I didn't know that.
You don't find that as racist? I think I do. I mean,
I do.
Yeah.
Did you not see? Did you not see? I will. Okay. I was like, here's the problem. This is my take on it. Is that I do think that's racist, and I think it's unacceptable. But I also recognize that in other parts of the world, they don't have the same relationship that we have here amongst the different cultures that are here. Because in the UK, it's really common. If you have an Irish friend, you'll go make some whiskey out of potatoes, you drunken bastard. You know, they make fun of each other based on their cultural stereotypes, because there's a sense of like, the difference between you and me is you live over there and I live over here. Because my parents live here and your parents lived over there. But, you know, and there's a real jocular sense to it. And so I wrote a message to Fiona where I explained with a certain amount of that white guy angst.
Oh yeah, yeah. I think I got that message. Yeah.
Yeah, because they don't understand. I think that some of them don't understand what happened here. The fact that you know, not my ancestors, but my ancestors, you know, other people's ancestors cleared the way for my ancestors. But basically, people came over. There were already people living here. They, you know, brought smallpox by accident, sort of. That's I don't. That's awful. And then the natives that didn't just get out of their way or die, they ended up having to shoot a whole bunch of them, right? That wasn't so much of a big problem here in Canada. Here in Canada, we made treaties with them and then turned around and broke the treaties. But then went to a totally different continent entirely and chained up and boated up a bunch of people and brought them in who didn't want to be here. Like, I mean, the context of North America and the race relations is a history of dehumanization. And anybody can say, well, oh, that was 300 years ago, but it's not, right? Because some of these things are still ongoing. When you see what life is like for natives in Canada, I don't want to comment on what life is like for natives in the States, because I don't know what reserves are like or what it's like when somebody doesn't live on the reserve. I don't know, but I can tell you they don't have nearly the same sort of freedom and lifestyle that other folks have here. The blacks don't have it so bad, but in the States, the blacks are getting shot by the police. Like, I don't understand what's going on here. And all I was trying to tell Fiona is, you might think it's funny. Actually, I think she appreciated because it was a gift from Saitan Atheist. And I think she appreciated the gift, but I just think she had to be told, I don't think you understand what the climate's like here. And honestly, when I wrote that message, I don't think that message had to be 10% as long as it was. I think all I had to do was tell her, you probably shouldn't do that, and she'd have taken it down anyway. But I ended up kind of launching into this big tirade about it, and some other people got pissed off. And anyway, sorry, go ahead.
Well, I was just going to say that we weren't intentionally looking at that, you know, for that. I think that when we were, because we were going to try to unblock her, we were seeing if she was blocked to see if she wanted to come in. So we were checking, we were screen sharing just to make sure everybody didn't have her blocked so that we can have her come in, and that just happened to be glanced at, and Veckel mentioned it, and I really didn't even think about it until he had mentioned that. But that's basically how it went down. It wasn't like people were, trying to point the finger at her or something, or look out.
You didn't seem offended, and I wasn't trying to take up the cause of being like, oh, poor Ronnie, because I don't think you were really offended by it. But that's not the point, right? It's not up to you to decide whether or not she can use this sort of. I mean, I don't think it's an accurate stereotype. Like, I don't know. Whatever. Let's not sort of dwell on that too much. It's just because I said the thing about the racism. No, G-Man has gone in a lot of hangouts lately and just accused people of being racist, just for the sake of calling people racist. I don't know what's going on there. I just sort of meant that in generality. I don't know that he's called Fiona a racist. I know he's called Jade Turkey Cat. He's called her a racist.
See, I'm not sure. I can't really talk about that because I don't know specifically which events he's calling people racist. So I don't know exactly what you're referring to. I know that that was the only events that I could think of to where he would be calling anybody racist.
I was just sort of making general comments about the conversation. Like, I'll tell you, someone I really like talking with is Arcane. He and I have done we've done 3 or 4 hangouts now, at least 4. 2 of them, just the 2 of us like this on my channel. And they've been great conversations, really well received by the audience. He and I had fun doing them. We argued a bit, disagreed about stuff. And I like the guy. We get along fine, except in the comments section. Anytime we get into a comment exchange, he's just like the biggest jerk. Yesterday he called me a nigger. Can you believe that? I didn't even know what to say. I typed just "shut up, honky." Like, I didn't even know what to say in response to that. Like, do you not like me enough to not call me a nigger, or was it a joke? Like, I don't understand what that even means. Like, you have no comment. I get it.
I don't know.
Yeah, I don't know. He gets weird in the comment section. But anyway, I hope that we can have more good conversations, and there's always going to be ponage, and there's always going to be talking shit Tuesdays and whatever else. But let's try to intersperse it with some actual conversations about the real topic.
Well,
that's all I ask.
I think that, well, since you brought up JD Kane's Hangouts, I think that there's actually a big problem with JD Kane's Hangouts, because we're talking about all this stuff. I might as well bring it up. What JD Kane's Hangouts, I noticed that there's this tendency, this pattern to where in JD Kane's Hangouts, I understand that they want to try to talk trash about people throughout the week, but whenever they're talking about events or people throughout the week, I noticed that when they are talking amongst each other, event and circumstances become so distorted from the truth. It's almost as if they're lying every week. I mean, in some cases, for example, I don't know if you want to consider this a lie, but this little situation to where we're talking about breaking down with assaults and stuff. I had explained to Fiona, and I had explained to Sam beforehand. Okay, I don't believe it's the same thing with the salts, because with salts in the cell, there's an established system there, and you have cytosol inside of the cytosol. You know, it's you got salts and you got things that are going to keep it protected. The mockery inside of the Hangouts, inside of the room, was more so like, well, True basically thinks that, you know, all life would be dissolved or would break down. You know, we wouldn't even be alive if we were going by what he's saying. Well, this was explained beforehand in the comments, so you know where my agreement was. You know what I was getting at. You know that I didn't say that. You know that I made a very clear distinction that, look, that's different in the cell because the cell has cytosol in it. But when they were talking amongst each other, it was like they didn't even know what I just said. They went on with what they wanted to say about it.
It was an unfair shortcut. Because you certainly didn't say, well, then it wouldn't work, because obviously it would, and it does, clearly. Well, I don't know. I mean, in terms of the lying, like I don't think, this is always a really strange issue between the sides here. I hear things from the more radical evangelicals that are demonstrably lies, especially lies about people. I don't know if I want to open a can of worms now to give some examples, but actually I'll do it in a vague way then, because I just don't want to get into a big argument about it. But about last year, or it was about 2 years ago, the Christian apologist on YouTube that accused another fairly famous atheist of abusing his son and his wife. And very quickly the story turned into that this Christian had said that he was beating his wife. This Christian never said that this atheist was beating his wife. He said he was abusing her. So, well, then he was just like, oh, I'm a victim here because everybody's falsely accusing me of saying that I falsely accused this guy of beating his wife. But he never acknowledged that it was a mistake to even say the guy was abusing his wife, which he wasn't. You know, just stuff like that. Whereas, you know, I hear you guys all the time say, like, I know our Kane and Pillbox are really big for saying, oh, well, you're lying. That guy's lying. He's lying. She's lying. Everybody's lying. And it's almost like they define a lie as being saying something that I personally don't agree with.
Well,
so I just want to say, if you have an example of a lie that was told on Talking Shit Tuesday, find me the timestamp, find me the video and the timestamp for it, and say how can you show that to be a lie? I know they say you don't agree with mischaracterization, certainly, but.
Well, I want to say first that two wrongs don't make a right. So if there's any Christians lying about anybody else, it's wrong. Either way, it's wrong. But I'm just saying that I think that, because we're talking about this, you know, basically the state of the great debate right now, right? Mm-hmm. And I think that personally think that JD Kane's Hangouts are dangerous for the state of the great debate. I think that his Hangouts do exactly what the problem is with the great debates, and it instigates tension between both sides, and it makes people just want to get at each other's throats and say, no, I didn't say anything like that. This is what I really said. And then you have these big groups of people and followings where they don't really care what the truth was. They'll pretty much just go along with what is said. I mean, for example, I mean, like I just brought up recently with what happened with Sam and Fiona and myself. They were clearly explained something in the comments, but they went about talking about it afterwards as if they didn't know what I just said. They were just like going with what they wanted to say, with my interpretation of what was being said. So I was like, you asked me about putting up some specific time frames. I was actually thinking about putting together a compilation type of video with a variety of different circumstances to where this has actually happened. So you might actually see something like that in the future.
I think those actually maybe I should address your more important point about it being dangerous. I do think there's a barbed nature to the show. I obviously don't hate it so much. I participated as much as my time permits, but I do recognize the potential for it making things worse when somebody's been causing a problem in the community, or you don't like what somebody's saying. And then you say, well, we're going to do a show where 20-25 minutes of the show are dedicated to talking about, you know, what a jerk this person is for doing that. I recognize the danger in that. The things that I don't like that happen is when it's if somebody's suffering a problem, like any sort of discussion about somebody that's got a mental health problem. For example, there was a guy recently who people have been saying, oh yeah, he's got some real mental health problems, and he was actually, during a hangout, the men in white coats literally showed up at his house, and he's like, oh, hang on a sec, and he walked away from his computer and left the mic open. You can actually hear in this hangout where this guy gets you know, gagged up and dragged away. And so if you, and not that they talked about that on Talking Shit Tuesday, but that was sort of one of the discussions. Well, is this something we should talk about? And like, no, you shouldn't. Anyway, sorry, I'm meandering a little bit. Is it dangerous? I think that there are some potential dangers there. I sort of have to let JD make his own grown-up decisions about what he wants to do on there. And I think for the most part, he makes the right choices. I don't think, like, I think when he picks on somebody, it's somebody who's just shown himself to be a lunkhead that just simply is not listening. But I also think he acknowledges mistakes. Like, there's an episode, you remember the one where he said G-Men's, somebody challenged him to say G-Men's first and last name 50 times on the show. And he did it, and I just, okay, well, I wouldn't have done that. He's
here's what I mean about what I'm saying. I mean, JD Kane, I'm on his Google Plus page right now. Here's how he starts off. Like this is his approach. This is like the standard approach that I see with some of the guys in his circle. I'm reading his little post right here. It says, "Hey, Biogenesis rant. This is for Ultra Owl, James Powers, TrueEmpiricism, Ernie Dever, G-Man, and anyone who has used the but abiogenesis is impossible because of X routine. You are effing idiots." Okay, so the approach is what? We are idiots or lunkheads because we don't agree that abiogenesis is possible. What is the X? How are we going to sort this out? If we're going to approach this great debate and just calling people's names or insulting people about things that we don't agree with, it's going to turn into a hostile environment. So, I mean, I think this type of attitude that JD Kane has, I mean, you can say, I mean, everybody tends to be a little bit arrogant or obnoxious at times, or so, you know, at some times, or even condescending when people are saying things that they don't agree with and they think that they're wrong about. You know, that's going to happen to an extent in these type of discussions, but insulting people and degrading people and calling them names because they don't agree with something that you don't agree with, that's wrong. I mean, what if they have some information that you don't have, or they can approach the situation in a way that you haven't looked at? You're automatically dismissing them. I mean, yeah, it's a hostile way to approach the situation, and it in no way at all makes this environment any better. It's instigating the problem that I've been complaining about for such a long time here online.
Yeah, I do think, actually I said we should end up a while ago, and I'm kind of glad we actually went on to this part of it, because I think actually I find this even more interesting than the whole phosphodiester bond topic. But although we really do have to wrap up soon, but I agree with you. I don't know if it should be different. You know what I mean? Like this isn't what we're doing here. When I say we, I mean, you know, me and JD and Dragnut and G-Man and you and let's include the Bible thumping wingnut crew that sort of, they don't really interact with us much. They're always very welcoming when I go over there, which is just not very often. They unfortunately hold it at the time when I'm generally pretty busy. But this whole discussion that goes on here, it's not a committee, it's not a corporation, it's not some sort of group that was impaneled to help save the world. We're a bunch of fucking idiots on YouTube, right? And why are we doing this? It's part of it is for fun. Now, we're also not just here to do stupid things and just treat each other like crap. I think it's neat that from this pointless thing that we do, some good things come out, right?
Yeah.
Like, like me having to look up the freaking nucleotide structure today, so I remember the phosphates where and the sugars what. We actually do encourage each other to learn things, and I just think that, I mean, you could say, well, it'd be better if we didn't insult each other so much, but I don't know, maybe it'd be too boring. I think that this community is always going to have that marbling, because I tell you something, that guy called me a nigger yesterday. And I called him, I said, shut up, honky, in response. And I can't figure out whether he was kidding or not. But I can tell you the next time he and I are in a hangout together, it's going to be a good hangout. And we're going to disagree with each other.
Mm-hmm.
And it's still going to be a good hangout. And I'll still wish him well. And I know he wishes me well. So it's weird, Ronnie. I just think that, I agree with your point, but I just don't know that it could be different. Or maybe it just shouldn't even be different. Maybe this is the way we got to be. I do think there are specific behaviors I really want to see a stop put to. Number one, false accusation. I want to see the false accusations just not happen. And people who do false accusations should just be chastised and derided to the point of humiliation and apology. That's really a problem, as far as I'm concerned. But
well, I agree. Well, I agree. I don't really have too much to say about that. I agree with that wholeheartedly. The main reason why is because I think that it's a little bit more than just having fun here online and having discussion. I think that it's the type of topics that we talk about, whether they be true or not, affects people on an emotional level and on a deeper level. There are some people who have dedicated their lives to believing in God, and insulting them and degrading them and saying things in a way that just put them down. And they're already in a position to what if they're intimidated? Okay, well, what if this guy is saying is true, and everything that I've lived for is wrong or something like that, and they're just coming by his post, and then he adds on to that emotion that they're feeling and just starts to call them names and beat them out. That's not the way to approach it. I think it's an immature way, and it shows that they don't understand, people that are acting like that, how it affects people on a deeper level, because they may be separated from you from across, different continents or whatever, but that doesn't mean that what you're saying to them will not have an effect on them. So, I mean, we can all have fun. We can all have discussions and talk about certain things, but it's very important to call people names and insult them and beat them down. It's good for you to challenge people's faith. I'd say that any Christian out there that isn't getting their faith challenged, that's a bad thing. It's good if there are atheists challenging things about things that you've never heard before or talked about. Don't get defensive when you hear people doing things like that, but I don't think that it's just unnecessary to attack somebody that could be in an emotional state already to begin with.
Yeah, and maybe we could end on this note, because I'll tell you, this is something I really I try to be mindful of in the discussion, is that there really should be an obvious imbalance in how serious we take these conversations, how to heart these things go, because let's say in terms of like unproven things that it's important to convince the other person of. Let's say that let's try to make this a parallel example here, is that I would try to convince you that evolution, specifically common ancestry, is true, that there's ample evidence that happened. Whether or not a God was behind that's a different discussion. But I would try to convince you that, look, you've really got to come to accept that dogs and cats have a common ancestor, an ancient, from the late Eocene common ancestor. And humans and orangutans and bonobo, we have a common ancestor, as we do with the cats and the dogs. I would want to convince you of that. On your side of it, you're trying to convince me of a creator God who has a plan for me, of a fallen world, of the gift of the sun and the torture and the death of the sun, paving a way for my salvation for eternity. The imbalance here being, Ronnie, I don't really give a shit if you ever come to believe in evolution. I think you should, because it's true, and you're probably smarter than you actually sound when you deny it. But I don't think you're going to do anything bad, or anything bad is going to happen to you because you don't believe in this set of scientific principles, right? It's certainly not as weird as being a flat earther, right? You'll be fine. I'm not worried about you. But I have to recognize at the same time that my rejection of what you're presenting, literally the gift of eternal salvation, that's important, right? In your view, you can't just say, oh, HogTie will be fine. So what? He doesn't believe Jesus is Lord. He'll be okay. I can wave my hand at you not believing in evolution, but I accept the fact that you guys can't be comfortable with me and my friends and my children not accepting God. So in this conversation, again, I want to wrap up on this point. In my conversation, I try to be respectful of the fact that this should be more important to you than it is to me. And I try to not be too flippant because of that imbalance.
Well, I don't really have too much to add other than I think that it depends on the person, I guess. So if some people don't really think of it on too much of a deep level in either direction, then maybe they won't really care. Some people, I believe that there are probably some atheists out there that they would probably prefer to believe in God than not to believe in God. But maybe they're not convinced with the answers, or the answers are not good enough. So everybody's different. Everybody's going to be approaching the situation a little bit different with each other. But I think that no matter what, the type of topics that we're talking about, that's not like talking about sports. These things affects people on a much a deeper level. We're not talking about just any random topic. That's it. That's all I really got to say.
Yeah, no, and I take your point there. My daughter's having a bit of a coughing fit there, but I take your point. Sometimes we do talk about sports, and it's okay then to be a little more jocular. But yeah, I think I see where it is. Okay, well, I want to thank you. I don't know what's happened. I mean, we've had some frictious interactions here in the last few months. It's good to kind of do a little bit of a hangout. And I think you've had some really good ones lately with, with Dave and with Fiona. A little less so with Sam. The one with Sam was kind of shouty. But so was there anything in this hangout, this is the last thing I want to ask you, was there anything in this hangout that brought you to a moment where you went, oh, I was wrong about that. I learned something today? I didn't think so.
Well, I don't know. I might have. I'd probably have to rewatch it. I can't remember every single thing we've talked about. We've been talking for about an hour, 2 hours or so.
Yeah, for a 1 hour hangout, we did pretty well with it. Well, I want to say thanks and have a good night. And to the viewers, to the viewers, about 20 minutes ago, I realized that I had turned on the online chat feature, meaning that up to that point, I'm sorry, I didn't know that you guys were discussing these interesting topics amongst yourselves, and perhaps for trying to tell me something. I should have announced at the beginning of the hangout that if you wanted to add something, you should send me a message on Google+. Having not done that, I didn't even check those messages. It was just me and Ronnie talking, and I ignored the whole rest of you. So as we now go off air, the comment section will open, and give it to the two of us with both barrels. So thanks for your attention. Have a good night, Ronnie. Oh, you stick around for a minute. We'll say our goodbyes, but say your good nights and off we go.
Goodbye.
All right.
Take it easy, guys.
And broadcast over here.